The liar paradox is one of the simplest and most thought-provoking puzzles in logic. It is a self-referential statement that creates a loop of contradiction. The classic example of the liar paradox is the statement, "This statement is false." On the surface, it seems harmless, but when you try to evaluate its truth, problems quickly arise. Let's examine what happens when we assume the statement is true. If "this statement is false" is true, then it must indeed be false because that is what it claims. But if it's false, then it cannot be true. This creates a contradiction because the truth of the statement depends on its own falsehood. No matter how you approach it, there is no way to resolve this self-referential conflict. The paradox becomes clearer when you consider the way truth and falsehood work. In most everyday statements, we can decide whether they are true or false based on evidence or logic. For example, the statement, "The sky is blue," can be verified by looking outside. But self-referential statements like, "This statement is false," do not reference an external fact. Instead, they refer only to themselves, creating a closed loop. The truth or falsehood of the statement depends entirely on itself, and that's where the problem lies. To understand why this is such a big deal, it helps to consider how we use language and logic. Language allows us to make claims about the world, and logic gives us rules for deciding whether those claims make sense. The liar paradox exposes a limitation in those rules. It shows that not all statements fit neatly into the categories of true or false. This challenges the foundation of how we think about truth and forces us to question the reliability of logical systems. Imagine a situation where someone says, "I am lying right now." This is a real-world version of the liar paradox. If the person is lying, then their claim that they are lying must be true. But if the claim is true, then they are not lying after all. Once again, we are stuck in a loop where no consistent answer is possible. This example highlights the paradox's ability to arise in everyday situations, not just in abstract philosophy. Philosophers have wrestled with the liar paradox for centuries. Ancient Greek philosopher Epimenides is often credited with one of the earliest versions. He supposedly declared, "All Cretans are liars." As a Cretan himself, Epimenides created a paradox. If all Cretans are liars, then his own statement must also be a lie, meaning not all Cretans are liars. This form of the paradox highlights the issue of self-reference and the challenge of determining whether a claim about truth can apply to itself. The liar paradox isn't just a curiosity, it has serious implications for logic and mathematics. In the early 20th century, mathematician and logician Kurt Gödel used a form of self-referential paradox to prove his famous incompleteness theorems. Gödel showed that in any sufficiently complex logical system, there will always be statements that are true but cannot be proven within the system. His work built on the ideas exposed by the liar paradox and demonstrated that even the most rigorous logical systems have limits. Computer science also grapples with versions of the liar paradox. In programming, a similar problem arises when trying to write a program that can determine whether another program will ever stop running. Alan Turing proved that it is impossible to create a general algorithm to solve this problem, known as the halting problem. Like the liar paradox, the halting problem reveals the boundaries of logical reasoning in systems that involve self-reference. One way to approach the paradox is to expand our understanding of truth. Traditional logic operates on the principle that every statement is either true or false. This is called the law of the excluded middle. The liar paradox suggests that some statements might not fit into this binary framework. Some logicians propose a third category for such statements, calling them undefined or indeterminate. This approach avoids the contradiction by refusing to classify the paradoxical statement as either true or false. Another approach involves distinguishing between different levels of language. In this view, the paradox arises because the statement blurs the line between speaking about the world and speaking about itself. By separating these levels, we can avoid the contradiction. For example, we might say that a statement about its own truth must be evaluated in a meta-language, a separate system that describes the original language. This strategy, known as Tarski's hierarchy, was developed by the logician Alfred Tarski as a way to deal with self-referential paradoxes. Despite these efforts, no solution to the liar paradox has been universally accepted. Each approach has its strengths and weaknesses, and the paradox continues to challenge our understanding of logic and language. Some philosophers embrace the paradox as a reminder that not all questions have simple answers. They argue that the liar paradox teaches us to be cautious about how we use language and to recognize the limits of logical reasoning. The paradox also invites us to think about the nature of self-reference more broadly. Self-referential structures appear in many areas of life, from art and literature to biology and technology. For example, M.C. Escher's drawings often depict impossible loops and recursive patterns, echoing the logic of the liar paradox. DNA replication in biology involves a kind of self-reference, as the molecule contains instructions for copying itself. Even social systems can exhibit self-referential dynamics, as when public opinion influences itself through feedback loops in media and communication. The liar paradox also sparks debates about the nature of truth. Some philosophers argue that truth is a human construct, shaped by the limitations of language and culture. From this perspective, the paradox reflects the imperfections of our tools for understanding the world. Others see truth as an objective property that exists independently of human thought. For them, the liar paradox is a puzzle to be solved, not a reflection of deeper limitations. In education, the liar paradox is often used to introduce students to the complexities of logic and philosophy. It provides a clear example of how simple statements can lead to deep questions. By grappling with the paradox, students learn to think critically about the assumptions underlying their reasoning. The paradox encourages curiosity and a willingness to question what seems obvious. The paradox also has practical implications for artificial intelligence and machine learning. As we design systems that process language and make decisions, we must ensure they can handle self-referential problems without getting stuck in infinite loops. The liar paradox reminds us that even simple logical structures can create challenges for automated reasoning. In summary, the liar paradox is a deceptively simple statement that reveals deep truths about logic, language, and thought. It challenges our understanding of truth and shows the limitations of binary reasoning. Over centuries, philosophers, mathematicians, and scientists have explored its implications, leading to new insights and approaches. Despite its age, the paradox remains as relevant as ever, continuing to provoke thought and inspire inquiry into the nature of truth and self-reference. Russell's paradox is one of the most important and intriguing discoveries in the history of logic and mathematics. It arises in set theory, which is the study of collections of objects, known as sets. Sets are fundamental to modern mathematics because they provide a way to organize and describe groups of elements. For example, a set might include all the numbers between 1 and 10, or all the books in a library. At first glance, the concept of a set seems simple, but Russell's paradox shows that this simplicity can lead to serious problems. The paradox is named after the British philosopher and logician Bertrand Russell, who discovered it in 1901. To understand the paradox, it helps to start with the idea of a set. A set can include any collection of objects, and those objects can be anything: numbers, animals, ideas, or even other sets. For example, you can have a set of all chairs in a room, or a set of all prime numbers less than 20. Sets are defined by a rule or property that determines which objects belong to them. Now consider the possibility of a set containing itself. Some sets are straightforward and do not contain themselves. For example, the set of all chairs does not include itself because the set itself is not a chair. However, other sets can contain themselves. Take the set of all sets. Since it is a set, it naturally includes itself as a member. Russell's paradox arises when we consider the set of all sets that do not contain themselves. Let's call this set R. By its definition, R includes all sets that do not include themselves as members. The question then becomes, does R contain itself? If R contains itself, then it must not contain itself, because it only includes sets that do not contain themselves. But if R does not contain itself, then it must contain itself, because it satisfies the condition of being a set that does not contain itself. This creates a contradiction. No matter how you try to resolve it, the definition of R leads to a logical loop with no consistent answer. The set of all sets that do not contain themselves cannot exist without breaking the rules of logic. This paradox is more than just a quirky puzzle. It exposed a fundamental problem in set theory. At the time, mathematicians were developing a framework for mathematics based on sets, using a system called naive set theory. In this system, it was assumed that any logical condition could define a set. Russell's paradox showed that this assumption leads to contradictions, undermining the entire foundation of set theory as it was understood. To appreciate the significance of the paradox, imagine if you built a house on a foundation that turned out to be unstable. Russell's paradox revealed that the foundation of mathematics had a major crack. If basic concepts like sets could lead to contradictions, then much of mathematics was at risk of collapsing. Russell's discovery prompted mathematicians to rethink set theory and develop new systems that avoided the paradox. One of the most influential responses came from Ernst Zermelo and Abraham Fraenkel, who developed the Zermelo-Fraenkel set theory, ZF, in the early 20th century. This system introduced restrictions on how sets could be defined. Instead of allowing any logical condition to define a set, ZF set theory imposed rules to ensure that problematic sets like R could not exist. One of these rules is the axiom of separation, which limits the kinds of subsets that can be formed. Another important response to Russell's paradox came from Bertrand Russell himself, along with his collaborator Alfred North Whitehead. They developed a system called type theory, which prevents self-referential sets by organizing objects into levels or types. In this system, a set can only include objects from a lower type, not objects of its own type. This prevents the kind of self-reference that leads to contradictions. Russell's paradox also had a significant impact on philosophy, especially in the study of logic and the nature of truth. It showed that even simple and seemingly obvious concepts like collection or set could lead to deep and unexpected problems. Philosophers began to explore questions about the limits of logic and the nature of self-reference. For example, if sets can lead to contradictions, what does this say about the reliability of human reasoning? How can we be sure that our logical systems are consistent? The paradox also influenced the work of Kurt Gödel, whose incompleteness theorems demonstrated that in any sufficiently complex mathematical system, there will always be true statements that cannot be proven within the system. Gödel's work built on the ideas exposed by Russell's paradox, showing that the limitations of logic and mathematics run even deeper than Russell had realized. In addition to its implications for mathematics and philosophy, Russell's paradox has practical applications in computer science. Many programming languages and database systems are based on logic and set theory, and they must avoid self-referential definitions to prevent errors. For example, if a database tried to include a category for all categories that do not include themselves, it could cause a system crash or infinite loop. By understanding and addressing the issues raised by Russell's paradox, computer scientists can design more robust systems. The paradox also has a broader cultural significance. It serves as a reminder that even the most basic ideas can lead to unexpected complications when examined closely. It challenges us to question our assumptions and to think critically about the frameworks we use to understand the world. The paradox shows that simplicity can be deceptive, and that even the most logical systems have limits. Russell's paradox remains a central topic in the philosophy of mathematics, and it continues to inspire new ideas and debates. Some philosophers argue that the paradox reveals a fundamental flaw in how we think about collections and categories. Others see it as a problem that can be resolved through careful definitions and restrictions. Regardless of one's perspective, the paradox is a powerful example of how a simple question, does the set of all sets that do not contain themselves contain itself, can lead to profound insights about logic, language, and reality. In conclusion, Russell's paradox is a cornerstone of modern logic and mathematics. It highlights the dangers of self-reference and the need for rigorous definitions in set theory. Its discovery reshaped the foundations of mathematics and led to the development of new systems that avoid contradictions. Beyond mathematics, it challenges us to think deeply about the nature of logic and the limits of human reasoning. Though it emerged more than a century ago, the paradox remains as relevant as ever, a timeless reminder of the complexity that can hide within seemingly simple ideas. The Barber Paradox is a classic logical puzzle that exposes a contradiction in the concept of self-reference. It was introduced by Bertrand Russell as a way to illustrate the problems with certain definitions in set theory, but it is presented as a simple and relatable story. At its heart, the paradox asks a seemingly straightforward question: can a barber exist who shaves all those and only those who do not shave themselves? While it sounds innocent, trying to answer the question leads to a logical contradiction. Imagine a small town with a barber who follows a strict rule. He shaves all the men in the town who do not shave themselves, and he shaves no one else. The puzzle then asks, who shaves the barber? This is where the trouble begins. If the barber shaves himself, he must belong to the group of men who shave themselves. But according to the rule, the barber only shaves men who do not shave themselves. Therefore, he cannot shave himself. On the other hand, if the barber does not shave himself, then he must fall into the group of men who do not shave themselves, which means the barber must shave him. This creates a contradiction. The barber cannot shave himself, but he also must shave himself. The paradox arises because the definition of the barber is self-referential. His existence depends on a rule that includes him in the group he is supposed to shave while also excluding him. No matter how you approach it, the barber's role cannot logically be fulfilled without breaking the rule. This makes the barber an impossible character, a figure whose existence is defined by a contradiction. To understand why this is a paradox, it helps to think about the nature of rules and definitions. Most rules work because they apply to a clear set of objects or people. For example, if we say, the barber shaves all the men in town with beards, the rule is easy to follow. The barber can simply shave everyone with a beard and ignore everyone else. But the rule in the Barber Paradox doesn't allow for this clarity. It tries to include the barber in a group defined by whether or not he shaves himself, which makes the rule self-contradictory. The Barber Paradox is closely related to Russell's paradox, which deals with sets that include or exclude themselves. In fact, the paradox was designed as an everyday analogy for Russell's discovery. In the Barber Paradox, the group of people in the town corresponds to a set, and the rule about who the barber shaves corresponds to the rule that defines the set. When the barber is added to the group, the same contradiction arises as in Russell's paradox. The paradox shows that self-reference can create logical loops that cannot be resolved. The implications of the Barber Paradox go beyond the story itself. It reveals a fundamental issue with how we think about categories and rules. Self-referential definitions, where something refers to itself in its own definition, often lead to contradictions. This is why mathematicians and logicians are careful to avoid self-reference when defining sets, systems, or logical frameworks. The Barber Paradox is a reminder that even simple rules can break down when they try to apply to themselves. One way to resolve the paradox is to conclude that the barber simply cannot exist. In this view, the rule that defines the barber is inherently flawed, and no person could fulfill the role without violating the rule. This aligns with how mathematicians address similar problems in set theory. They introduced restrictions to prevent self-referential definitions, ensuring that sets like the barber's group could not exist. Another way to think about the paradox is to question whether it makes sense to define a barber in this way at all. In the real world, no one would expect a barber to follow such a rigid and contradictory rule. The paradox is purely hypothetical, designed to highlight a problem with logic rather than to describe a real situation. By recognizing the absurdity of the scenario, we can see the paradox as a tool for understanding logical limits rather than a practical puzzle to solve. The Barber Paradox also raises interesting philosophical questions about identity and roles. In the story, the barber's identity is entirely defined by the rule about who he shaves. But in real life, people are more than the roles they play. A barber might shave some people and not others for many reasons, none of which need to create contradictions. The paradox simplifies the barber's role to the point of absurdity, which is why it leads to a logical breakdown. Despite its simplicity, the Barber Paradox has practical applications in fields like computer science and artificial intelligence. Self-referential problems can arise in programming when a system is asked to process information about itself. For example, a computer program might encounter an error if it tries to analyze its own code in a way that leads to infinite recursion. The Barber Paradox is a reminder that systems need clear and consistent rules to avoid contradictions. In addition to its logical implications, the Barber Paradox has a cultural appeal because of its simplicity and humor. The image of a barber caught in a logical loop, unable to decide whether to shave himself or not, is both amusing and thought-provoking. It's an example of how abstract ideas can be made accessible through storytelling, inviting people to explore complex concepts in a relatable way. The paradox also invites reflection on the limitations of language. The rule about who the barber shaves seems clear at first, but it falls apart under scrutiny. This shows that language, while powerful, is not always precise enough to handle self-referential definitions. The Barber Paradox reminds us to be cautious when using language to define concepts, especially when those concepts involve self-reference. Ultimately, the Barber Paradox is a lesson in the power and pitfalls of logic. It illustrates how simple ideas can lead to profound questions and challenges us to think critically about the systems we use to organize the world. While the paradox may seem like a playful thought experiment, it has deep connections to the foundations of mathematics, philosophy, and science. By exploring its implications, we gain a better understanding of the limits of logic and the importance of clear, consistent definitions. In summary, the Barber Paradox is a timeless puzzle that reveals the contradictions inherent in self-referential definitions. It serves as a vivid example of how logical systems can break down when they try to include themselves. Through its simplicity and humor, the paradox continues to inspire curiosity and exploration, reminding us that even the most basic concepts can lead to surprising and profound insights. Zeno's paradoxes are a series of philosophical puzzles that challenge our understanding of motion, space, and time. They were introduced by Zeno of Elea, a Greek philosopher who lived in the 5th century BCE. Zeno's goal was to defend the teachings of his mentor, Parmenides, who argued that change and motion are illusions. Through his paradoxes, Zeno sought to show that the concept of motion leads to contradictions, making it impossible. While these paradoxes seem simple, they pose deep questions about how we think about the physical world and mathematics. One of the most famous paradoxes is Achilles and the tortoise. In this scenario, the great warrior Achilles races a tortoise. To give the tortoise a head start, Achilles begins the race some distance behind. The paradox states that Achilles can never catch up to the tortoise, even though he is much faster. Here's why. As Achilles reaches the spot where the tortoise started, the tortoise has moved a little farther ahead. When Achilles reaches that new spot, the tortoise has moved again. This process continues infinitely, with Achilles getting closer to the tortoise but never quite overtaking it. The paradox suggests that motion itself is impossible because it involves completing an infinite number of steps. At first glance, this reasoning seems absurd. We know from experience that faster runners overtake slower ones all the time. So why does Zeno's argument feel so convincing? The key lies in the idea of dividing motion into infinitely many steps. By focusing on each individual step, the paradox creates the illusion that Achilles can never reach the tortoise, even though the distance between them is shrinking. To understand the paradox, it helps to think about the concept of infinity. In Zeno's time, the idea of infinity was not well understood, and people found it difficult to imagine completing an infinite process. The paradox exploits this confusion by suggesting that an infinite number of steps cannot be completed in a finite amount of time. However, modern mathematics provides tools to address this issue. Using the concept of limits, we can show that the total time required for Achilles to catch the tortoise is finite, even though the number of steps is infinite. The paradox is resolved mathematically, but it still challenges our intuition about how motion works. Another of Zeno's paradoxes is the Dichotomy Paradox. This puzzle argues that motion is impossible because to travel any distance, you must first travel half that distance. Before reaching the halfway point, you must travel half of that distance, and so on. This creates an infinite series of smaller and smaller steps that must be completed before reaching the destination. Since there are infinitely many steps, Zeno concludes that it is impossible to complete them all, and therefore motion cannot occur. Like Achilles and the tortoise, the Dichotomy Paradox relies on dividing motion into an infinite sequence. It highlights the challenge of understanding how infinite processes can occur in finite time. Modern mathematics addresses this paradox through the concept of convergent series. When we add up the infinite sequence of smaller distances, the total sum is finite. For example, if you start with a distance of 1 and keep halving it, the series converges to 1. This mathematical insight resolves the paradox, but it also raises deeper questions about how we experience time and space. Zeno's arrow paradox offers another perspective on the nature of motion. Imagine an arrow in flight. At any single instant, the arrow is not moving. It occupies a fixed position in space. If time is made up of a series of instants, and the arrow is stationary in each instant, then how can it ever move? Zeno concludes that motion is an illusion because it cannot be explained in terms of individual moments. This paradox challenges our understanding of time. It assumes that time is composed of discrete instants, like frames in a film. If each frame is static, then motion seems impossible. Modern physics and philosophy offer different ways to address this issue. Some theories suggest that time is continuous, not discrete, meaning there are no individual frames to analyze. Others argue that motion arises from the relationships between objects over time, rather than being something that happens in isolated moments. Zeno's stadium paradox is another example of his clever reasoning. Imagine two rows of objects moving past each other in opposite directions, with a stationary row in the middle. Zeno argues that the relative motion between the moving rows creates a contradiction. If we measure the motion relative to the stationary row, everything seems normal. But if we measure the motion of one row relative to the other, the distances don't add up consistently. This paradox raises questions about how we measure and understand relative motion. What makes Zeno's paradoxes so fascinating is their ability to reveal hidden assumptions in our thinking. At first glance, the paradoxes seem to prove that motion is impossible, but when we examine them more closely, we realize they depend on certain ideas about infinity, time, and space. By questioning these ideas, Zeno forces us to think more carefully about the nature of reality. Zeno's paradoxes also highlight the difference between how we experience the world and how we describe it mathematically. In everyday life, we see objects moving and assume that motion is straightforward. But when we analyze motion mathematically, we encounter complexities that are not immediately obvious. The paradoxes remind us that even the simplest concepts, like moving from one place to another, can be surprisingly difficult to define. Over the centuries, Zeno's paradoxes have inspired mathematicians, philosophers, and scientists to explore new ideas. In the 17th century, the development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz provided a mathematical framework for dealing with infinite processes. Calculus allows us to calculate the total distance or time involved in an infinite series, resolving many of the issues raised by Zeno. However, the paradoxes continue to provoke philosophical debates about the nature of infinity and the relationship between mathematics and the physical world. In modern physics, Zeno's paradoxes intersect with questions about the nature of space and time. For example, quantum mechanics suggests that space and time may not be continuous, but instead made up of discrete units at the smallest scales. This idea challenges the classical view of motion and raises new questions about how Zeno's arguments apply in the context of quantum theory. Similarly, the theory of relativity shows that time and space are interconnected and relative, further complicating our understanding of motion. Zeno's paradoxes also have implications for artificial intelligence and computer science. Algorithms that deal with infinite processes, such as iterative calculations or simulations, must address issues similar to those raised by Zeno. Understanding how to manage infinite sequences and convergent series is essential for designing efficient and accurate computational systems. Despite the advances in mathematics and science, Zeno's paradoxes remain relevant and thought-provoking. They remind us that our understanding of the world is shaped by the tools and concepts we use to describe it. By challenging these tools, Zeno encourages us to question our assumptions and seek deeper insights. In summary, Zeno's paradoxes are a collection of puzzles that challenge our understanding of motion, time, and infinity. From Achilles and the tortoise to the Dichotomy Paradox, these puzzles highlight the complexities of concepts we often take for granted. While modern mathematics resolves many of the paradoxes, they continue to inspire new questions and ideas. Zeno's work is a timeless reminder of the power of philosophical inquiry and the importance of examining even the most basic aspects of our reality. The paradox of the unexpected hanging is a fascinating and puzzling scenario that challenges our understanding of logic, knowledge, and expectations. It is a thought experiment that reveals how reasoning can lead to surprising contradictions, even when it seems sound. The paradox is not just a curiosity. It raises deep questions about the nature of prediction, self-reference, and the limits of human understanding. The paradox begins with a judge sentencing a prisoner. The judge declares that the prisoner will be hanged at noon on one weekday in the following week, but the execution will come as a surprise. The prisoner will not know the day of the hanging until the executioner arrives. The prisoner, who has time to think through the judge's statement, believes he can avoid the surprise and concludes that the hanging cannot happen at all. However, the paradox lies in the prisoner's reasoning and the unexpected nature of the event. To understand the paradox, let's examine the prisoner's thought process. He starts by considering the possibility of the hanging occurring on Friday, the last day of the week. If the hanging hasn't happened by Thursday evening, he reasons, then it must happen on Friday. But if he knows this in advance, the hanging on Friday won't be a surprise. Therefore, the prisoner concludes the hanging cannot happen on Friday. Next, the prisoner considers Thursday. Since Friday has been eliminated, he reasons that if the hanging hasn't occurred by Wednesday evening, it must happen on Thursday. But if he can predict that, the hanging on Thursday won't be a surprise either. Using similar logic, the prisoner eliminates Wednesday, Tuesday, and finally Monday, concluding that the hanging cannot occur on any day of the week without violating the judge's condition of surprise. Feeling confident in his reasoning, the prisoner relaxes, believing he has outsmarted the judge. However, the executioner arrives unexpectedly on, say, Wednesday, and the prisoner is hanged. Despite all his logical deductions, the hanging is a complete surprise, just as the judge promised. This is the heart of the paradox. The prisoner's reasoning seems flawless, yet it leads to a conclusion that is proven wrong. The paradox challenges our understanding of logic because the prisoner's argument appears valid when taken step by step. Each elimination seems reasonable, yet the conclusion that the hanging cannot occur is clearly incorrect. The paradox highlights a conflict between two ideas: the ability to predict future events based on logic and the idea of an event being truly surprising. One way to approach the paradox is to question the definition of surprise. The prisoner assumes that if he can logically predict the hanging on a specific day, it cannot be a surprise. However, this definition is problematic. In the context of the paradox, surprise depends not just on the prisoner's logical deductions, but also on his actual state of knowledge when the executioner arrives. Even if the prisoner has considered every possibility, the actual moment of realization can still catch him off guard. Another approach to the paradox involves self-reference. The judge's statement about the hanging refers to the prisoner's expectations, creating a loop where the prisoner's reasoning affects the very conditions of the event. This self-referential structure is similar to other paradoxes, such as the liar paradox, where a statement's truth depends on its own falsity. In the case of the unexpected hanging, the prisoner's reasoning undermines his ability to anticipate the event, allowing the judge's condition of surprise to be fulfilled. The paradox also raises questions about the nature of prediction and knowledge. The prisoner's reasoning relies on the assumption that he can predict the hanging with certainty. However, this assumption overlooks the possibility that his reasoning might itself create the conditions for the surprise. By overthinking the situation, the prisoner blinds himself to the unpredictability of real events. This suggests that not all situations can be fully understood or predicted through logic alone. Philosophers and logicians have debated the unexpected hanging paradox for decades, and it has inspired a variety of interpretations and responses. Some argue that the paradox exposes the limitations of human reasoning, showing that certain scenarios cannot be fully analyzed without leading to contradictions. Others view the paradox as a problem of language, where the judge's statement creates confusion because it mixes logical reasoning with psychological concepts like surprise. The paradox also has practical implications in areas such as decision-making and game theory. It illustrates how assumptions about knowledge and prediction can influence outcomes. For example, in strategic situations where one party tries to outguess another, the act of reasoning about the other's intentions can create unexpected results. The paradox reminds us that overanalyzing a situation can sometimes lead to flawed conclusions. In addition to its philosophical significance, the paradox has a psychological dimension. It plays on the tension between certainty and uncertainty, challenging the prisoner to reconcile his logical reasoning with the unpredictable nature of the world. This mirrors real-life situations where people try to anticipate events, only to be surprised when things unfold differently. The paradox highlights the limits of control and the inevitability of the unexpected. The unexpected hanging paradox also invites reflection on the relationship between logic and human experience. While logic provides a powerful tool for understanding the world, it is not always sufficient to capture the complexity of real-life situations. The paradox shows that even the most rigorous reasoning can fail when it encounters concepts like surprise, which involve subjective and emotional factors. Over the years, the paradox has been adapted into other forms, such as the surprise exam paradox. In this version, a teacher announces that there will be a surprise test during the week, leading students to engage in similar reasoning to the prisoner. Like the hanging, the test arrives unexpectedly, despite the student's attempts to predict it. These variations show the versatility of the paradox and its ability to illuminate different aspects of logic and human thought. In summary, the paradox of the unexpected hanging is a powerful and thought-provoking puzzle that challenges our understanding of logic, knowledge, and expectations. It demonstrates how reasoning can lead to contradictions when it encounters concepts like surprise and self-reference. The paradox raises important questions about the nature of prediction and the limits of human understanding, reminding us that the world often defies our expectations. Through its simplicity and depth, the paradox continues to inspire curiosity and debate, making it a timeless exploration of the complexities of logic and human experience. The Bootstrap Paradox is a puzzling scenario that arises in discussions about time travel, causality, and the nature of information. It is a thought experiment that challenges our understanding of how events can be connected and how cause and effect operate when time travel is involved. At its core, the paradox describes a situation where an object, piece of information, or idea exists without an identifiable origin. It appears to come into existence out of nowhere, creating a loop in time where the origin of the object or idea is lost. To understand the Bootstrap Paradox, let's consider a simple example involving an inventor and a time machine. Imagine an inventor in the year 2050 who discovers the plans for a time machine in a dusty old notebook. The inventor builds the time machine using these plans and then travels back in time to 2020. While in the past, the inventor leaves the plans in the exact place where they will later be discovered in 2050. The plans complete a loop. They travel from 2050 to 2020 and then back to 2050. The question is, who originally created the plans? The plans seem to exist without ever having been created by anyone, which defies our usual understanding of causality. The paradox gets its name from the idea of pulling yourself up by your own bootstraps, an impossible feat that illustrates the self-referential nature of the scenario. In the Bootstrap Paradox, an object or piece of information essentially pulls itself into existence. It exists because it exists, without any clear beginning or origin. This circular logic creates a situation that seems logically consistent at first glance, but breaks down when you try to trace the timeline in a straightforward way. Another popular example of the Bootstrap Paradox involves a time traveler and William Shakespeare. Imagine a time traveler who loves Shakespeare's plays and decides to visit the past to meet the famous playwright. The time traveler brings a copy of Shakespeare's complete works to the 16th century and gives it to him. Shakespeare, impressed by the book, publishes the plays under his own name, becoming the celebrated author we know today. Centuries later, the time traveler discovers Shakespeare's works, becomes inspired by them, and decides to take a copy back in time to meet him. Once again, we are left with a loop. The plays exist, but their origin is unclear. Did Shakespeare write them, or did the time traveler bring them back from the future? The Bootstrap Paradox raises profound questions about the nature of causality. In our everyday understanding of the world, cause precedes effect. An event happens because something else caused it to happen. A tree grows from a seed, which comes from another tree. There is always a chain of events leading back to an identifiable starting point. The Bootstrap Paradox disrupts this chain by creating a loop where cause and effect are indistinguishable. The object or idea exists, but it is not clear where or when it came into being. This paradox also challenges our understanding of information. In the example of Shakespeare, the plays exist without an original author. They are passed from the time traveler to Shakespeare and back to the time traveler, forming a closed loop. This raises the question of whether information can exist without being created. In the real world, every book, song, or idea has an origin, a moment when it was first conceived. The Bootstrap Paradox suggests a scenario where information appears to exist independently of any creator, which defies our usual understanding of how knowledge is produced and transmitted. The paradox also has implications for physics and the study of time travel. In theoretical physics, time travel is often discussed in the context of general relativity, which allows for the possibility of closed time-like curves, CTCs. These curves describe paths through space-time that loop back on themselves, potentially allowing objects or information to travel back in time. The Bootstrap Paradox is one example of the strange consequences that can arise in a universe where CTCs exist. It highlights the challenges of maintaining consistent causality in such a scenario and raises questions about the nature of time itself. One way to approach the paradox is to consider the possibility that our understanding of causality might be incomplete. In a universe where time travel is possible, the usual rules of cause and effect may not apply in the same way. Some physicists and philosophers suggest that time travel could involve a form of consistent self-creation, where objects and information can exist in loops without violating the laws of physics. This idea is speculative, but it offers a way to think about the paradox without rejecting the possibility of time travel altogether. Another approach is to question whether the Bootstrap Paradox represents a genuine problem or simply a limitation of our perspective. In the examples we've discussed, the paradox arises because we are trying to impose a linear understanding of time on a situation that is inherently nonlinear. If we accept that time can loop back on itself, then the existence of objects and information in such loops might not be paradoxical at all. Instead, it could be a natural consequence of a universe where time is more flexible than we currently understand. The paradox also invites us to think about the role of free will and agency in time travel. If a time traveler brings Shakespeare's plays to the past, does that mean the time traveler is the true author of the plays? Or does the act of bringing them back erase the distinction between author and messenger? The Bootstrap Paradox blurs the lines between creator and recipient, challenging our assumptions about how ideas and innovations are generated. Despite its speculative nature, the Bootstrap Paradox has inspired countless stories in science fiction, from novels to movies to television shows. It captures the imagination because it combines the wonder of time travel with the deep philosophical questions it raises. Stories that explore the paradox often use it to highlight the strange and unexpected consequences of tampering with the timeline. They remind us that even seemingly simple actions can create complex and unpredictable loops. In real-world science, the paradox serves as a thought experiment to explore the limits of our understanding of time and causality. While time travel remains purely theoretical, the paradox helps physicists and philosophers think through the implications of such a phenomenon. It pushes the boundaries of what we know and challenges us to consider new possibilities for how the universe might work. In conclusion, the Bootstrap Paradox is a thought-provoking puzzle that challenges our understanding of causality, information, and time. It describes situations where objects or ideas exist without a clear origin, forming self-contained loops that defy traditional logic. Through its examples, like the time traveler in Shakespeare, the paradox illustrates the strange consequences of time travel and raises deep questions about the nature of reality. While it may remain a topic of speculation, the Bootstrap Paradox continues to inspire curiosity and exploration, reminding us of the mysteries that still lie at the edges of our knowledge. The paradox of the ravens, also known as Hempel's paradox, is a thought experiment that explores the nature of evidence and how we confirm statements or hypotheses. First introduced by philosopher Carl Gustav Hempel in the 1940s, it challenges our intuition about what counts as evidence and highlights the complexities of reasoning and scientific inquiry. While the paradox seems straightforward at first, it quickly reveals deeper questions about logic, probability, and how we draw conclusions about the world. To understand the paradox, let's start with a simple hypothesis. All ravens are black. This is a general statement about ravens, meaning every raven, without exception, must be black for the statement to be true. In science and logic, we typically confirm such statements by observing examples that fit the hypothesis. For instance, if you see a black raven, that observation seems to support the idea that all ravens are black. Now comes the twist. In logic, statements are often treated as logically equivalent if they mean the same thing. The statement "all ravens are black" is logically equivalent to the statement "if something is not black, then it is not a raven." These two statements say the same thing in different ways. If you find a raven that is not black, you've disproven both statements. Similarly, if you confirm that everything not black is not a raven, you've supported the idea that all ravens are black. Here's where the paradox arises. According to the equivalence, observing anything that is not black and not a raven should count as evidence for the hypothesis all ravens are black. For example, if you see a green apple, you've observed something that is not black, the apple is green, and is not a raven, it's an apple. By the logic of equivalence, this observation supports the idea that all ravens are black. Intuitively, this feels absurd. How can looking at a green apple tell us anything about ravens? The paradox lies in the apparent contradiction between what logic tells us and what our intuition suggests. Logic says that observing a green apple provides evidence for the hypothesis, but our intuition tells us that such evidence is irrelevant. After all, green apples have nothing to do with ravens. This disconnect forces us to question how we define evidence and whether our reasoning about confirmation is as straightforward as we assume. To unpack the paradox, it helps to think about the idea of evidence in more detail. When we observe a black raven, it seems like direct evidence for the hypothesis because it aligns with what the hypothesis predicts. In contrast, observing a green apple feels irrelevant because it doesn't seem to connect to ravens at all. The paradox challenges us to reconcile these different intuitions about what counts as evidence. One way to approach the paradox is through the concept of relevance. While it's true that observing a green apple technically supports the hypothesis all ravens are black, the degree of support it provides is extremely small. In the vast universe of objects, there are countless things that are not black and not ravens: green apples, red chairs, blue cars, and so on. Observing one more such object doesn't significantly change our confidence in the hypothesis. In contrast, observing a black raven directly engages with the central claim of the hypothesis and provides stronger support. This idea connects to the concept of Bayesian reasoning, a framework for understanding how evidence updates our beliefs. In Bayesian terms, the degree to which a piece of evidence supports a hypothesis depends on how much it changes the probability of the hypothesis being true. Observing a black raven increases the probability that all ravens are black because it directly confirms the prediction. Observing a green apple, while technically evidence, changes the probability so slightly that its impact is negligible. Another perspective on the paradox involves the distinction between logical equivalence and practical relevance. While all ravens are black, and if something is not black, then it is not a raven, are logically equivalent, they emphasize different aspects of the world. The first statement focuses on the properties of ravens, while the second focuses on the relationship between ravens and other objects. The paradox arises because we tend to think about evidence in terms of practical relevance rather than pure logic. In practical terms, evidence about ravens feels more relevant to the hypothesis than evidence about apples. Philosophers have also explored the role of background knowledge in resolving the paradox. Our existing knowledge about the world influences how we interpret evidence. We know that apples and ravens are unrelated, so we instinctively dismiss the idea that observing a green apple tells us anything about ravens. This background knowledge shapes our intuitions and helps us navigate the paradox, even if the logical equivalence remains intact. The paradox of the ravens has important implications for science and reasoning. It highlights the complexities of confirmation and reminds us that evidence is not always as straightforward as it seems. Scientists often rely on observations to confirm hypotheses, but the paradox shows that the relationship between evidence and hypotheses can be more nuanced than we realize. It encourages us to think critically about how we gather and interpret data, and to be mindful of the assumptions underlying our reasoning. The paradox also raises broader questions about the nature of logic and human understanding. Logic provides powerful tools for reasoning, but it doesn't always align with our intuitions or practical concerns. The paradox of the ravens shows that purely logical reasoning can sometimes lead to conclusions that feel counterintuitive or irrelevant. This tension between logic and intuition is a recurring theme in philosophy, reminding us that our understanding of the world is shaped by both formal reasoning and human experience. Despite its abstract nature, the paradox of the ravens has practical applications. It serves as a reminder to consider the relevance and context of evidence in decision-making. In fields like medicine, law, and policy, evidence plays a crucial role in shaping decisions. Understanding the complexities of evidence, as illustrated by the paradox, can help us avoid pitfalls and make better informed choices. The paradox also has educational value. It introduces students to the subtleties of logic and scientific reasoning, encouraging them to think critically about what counts as evidence and why. By grappling with the paradox, students learn to question their assumptions and develop a deeper understanding of the relationship between logic, evidence, and knowledge. In summary, the paradox of the ravens is a thought-provoking puzzle that challenges our understanding of evidence and confirmation. It highlights the tension between logical reasoning and practical relevance, forcing us to reconsider how we define and evaluate evidence. While the paradox can be resolved through concepts like Bayesian reasoning and background knowledge, it continues to inspire philosophical debate and reflection. By exploring the paradox, we gain valuable insights into the complexities of logic, science, and human understanding, reminding us that even the simplest ideas can lead to profound questions. The Sorites paradox, also known as the paradox of the heap, is a classic puzzle in philosophy and logic that challenges our understanding of vague concepts and how we define them. It is a deceptively simple thought experiment that raises deep questions about language, reasoning, and the boundaries of categories. The paradox gets its name from the Greek word soros, meaning heap, and it focuses on the problem of determining when a collection of objects like grains of sand becomes a heap. The paradox begins with a simple scenario. Imagine a single grain of sand. Clearly, one grain of sand is not a heap. Now suppose you add another grain of sand. 2 grains still do not seem to make a heap. Add a third grain, then a fourth, and so on. At what point do the grains of sand become a heap? There seems to be no clear answer. If one grain is not enough to make a heap, and adding a single grain does not turn a non-heap into a heap, then no matter how many grains you add, it appears that you can never form a heap. This conclusion feels absurd because we know that a pile of sand with thousands of grains is obviously a heap. Yet the reasoning suggests otherwise. The paradox hinges on the vagueness of the concept of a heap. Words like heap are vague because they lack precise boundaries. There is no clear number of grains of sand that marks the transition from not a heap to a heap. This vagueness creates a slippery slope. If we can't pinpoint the exact moment when a heap is formed, then the distinction between heaps and non-heaps seems arbitrary or even meaningless. To make the paradox more concrete, consider another example, the concept of baldness. Suppose someone has a full head of hair. Clearly, this person is not bald. Now imagine removing one hair at a time. Losing a single hair does not make someone bald, but if you continue this process, eventually the person will be bald. At what exact point does the transition occur? Like the heap, baldness is a vague concept with no precise threshold. The Sorites paradox applies to many everyday concepts, not just heaps or baldness. It arises whenever we deal with vague terms like tall, rich, old, or expensive. For example, how much money does someone need to be considered rich? Is there a specific dollar amount that defines wealth? If not, the concept of rich becomes just as slippery as the concept of a heap. These vague terms are an essential part of human language, but they resist the kind of precise definitions we often expect in logic and science. Philosophers have proposed various ways to address the Sorites paradox, but none of them is entirely satisfying. One approach is to accept that vague terms are inherently imprecise, and that trying to draw sharp boundaries is futile. From this perspective, the paradox is not a flaw in logic, but a reflection of how language works. Vagueness allows us to use words flexibly and adapt them to different contexts, even if it leads to occasional puzzles like the Sorites paradox. Another approach involves introducing the concept of fuzzy logic. In traditional logic, a statement is either true or false with no middle ground. Fuzzy logic, however, allows for degrees of truth. Under this framework, a small pile of sand might be 10% a heap, while a larger pile might be 50% a heap, and so on. This approach acknowledges that vague terms represent a spectrum rather than a binary distinction. While fuzzy logic resolves some aspects of the paradox, it also complicates our understanding of truth and challenges the binary logic that underpins much of philosophy and mathematics. A different solution involves the idea of supervaluationism. This approach suggests that vague terms have multiple acceptable interpretations, each with its own boundaries. For example, some interpretations might define a heap as 100 grains of sand or more, while others might set the threshold at 200 grains. According to supervaluationism, a statement like, "This is a heap," is true if it holds under all acceptable interpretations and false if it fails under all of them. If the interpretations disagree, the statement is neither true nor false, but indeterminate. This approach preserves the idea that vagueness is a feature of language, not a failure of logic. Some philosophers take a more radical stance, arguing that the Sorites paradox exposes fundamental problems with how we think about categories and definitions. They suggest that our tendency to seek sharp boundaries for vague concepts is misguided. Instead, we should embrace the idea that some distinctions are inherently blurry and resist the urge to impose artificial precision. The Sorites paradox also has practical implications. In law, medicine, and public policy, vague terms often play a crucial role. For example, laws may define categories like juvenile, disabled, or dangerous without specifying exact thresholds. This vagueness allows for flexibility and interpretation, but it also creates challenges. Where should we draw the line? Who gets to decide? The Sorites paradox reminds us that these decisions are not always straightforward, and that vague terms can lead to difficult debates about fairness and consistency. In science, the paradox raises questions about classification and measurement. Biologists, for instance, often deal with categories like species or ecosystem, which can be surprisingly difficult to define precisely. Similarly, psychologists grapple with terms like intelligence or mental illness, which are subject to interpretation and debate. The Sorites paradox highlights the need for clear definitions while acknowledging the limitations of precision in certain contexts. In everyday life, the paradox challenges us to think critically about the words we use and the assumptions we make. It reminds us that language is not always as precise as we might like, and that some concepts are inherently fuzzy. By recognizing the limitations of vague terms, we can navigate these ambiguities more thoughtfully and avoid being misled by simplistic reasoning. The paradox also invites reflection on the nature of reasoning itself. It shows that even simple and intuitive ideas, like adding grains of sand to form a heap, can lead to surprising complexities when analyzed closely. This tension between intuition and logic is a recurring theme in philosophy, reminding us that our understanding of the world is often shaped by both formal reasoning and everyday experience. In summary, the Sorites paradox is a powerful thought experiment that challenges our understanding of vagueness and categorization. It reveals the difficulties of defining concepts like heap, bald, or rich, and forces us to confront the limitations of language and logic. While philosophers have proposed various solutions, the paradox remains a vivid reminder of the complexities of reasoning and the ambiguities of human thought. By exploring the Sorites paradox, we gain a deeper appreciation for the richness of language and the challenges of navigating a world that often resists precise definitions. Self-referential statements are statements that refer to themselves in some way. They may seem simple or harmless at first glance, but they often reveal deep and puzzling questions about logic, language, and truth. These statements can lead to contradictions, infinite loops, or paradoxes that defy easy explanation. To understand them better, let's break down what they are, why they matter, and how they can challenge our assumptions about reasoning and meaning. A basic example of a self-referential statement is the classic, "This statement is false." On the surface, it's just a sentence, but when you try to determine whether it's true or false, you run into trouble. If the statement is true, then it must be false, as it claims. But if it's false, then it must be true because it accurately describes its falsity. There's no stable way to assign it a truth value. This creates a paradox. The self-reference in this example is direct and explicit. The statement points back to itself, creating a loop. You could think of it as a snake eating its tail, a process that has no natural stopping point. It keeps turning back on itself, endlessly. Philosophers have studied this type of paradox for centuries, and it continues to be a central topic in discussions about logic and language. There are other forms of self-referential statements that can also cause confusion or raise interesting questions. For instance, consider, "This sentence is incomplete because..." It's unfinished, yet it claims to explain its own incompleteness. Reading it, you might pause and wonder how to interpret it. Is it truly incomplete, or does its incompleteness somehow make it complete? The ambiguity here stems from its self-referential nature, forcing you to think about the relationship between meaning and structure. Another famous example is the statement, "This sentence is true." At first, it seems harmless because it declares its own truth. However, it doesn't provide any external reason or evidence for its truth. It's a circular declaration, true because it says it is true. This lack of external grounding makes some people uneasy. What does it mean for something to be true if its only justification is itself? It's not a paradox in the same way as "this statement is false," but it raises philosophical questions about how we define and understand truth. Self-referential statements don't always involve truth or falsity. Sometimes they refer to other properties of language or logic. For example, "This statement is written in English" is a self-referential statement about the language it uses. This one is easy to verify. You can see that it's written in English. There's no paradox here, just a straightforward observation. Yet even this simple example hints at the versatility and complexity of self-reference. It shows how a statement can turn its focus inward, examining itself rather than something external. Not all self-referential statements are sentences or phrases. Self-reference appears in many areas, including mathematics, computer science, and art. In mathematics, for instance, Kurt Gödel's incompleteness theorems rely on self-referential constructions. Gödel showed that in any sufficiently complex mathematical system, there are true statements that cannot be proven within the system. He did this by creating a statement that essentially says, "This statement cannot be proven." The result is a mathematical version of the self-referential paradoxes found in language. with profound implications for the limits of formal systems. In computer science, self-reference is central to recursion, a technique where a function calls itself to solve smaller instances of a problem. Recursion is powerful and useful, but if not handled carefully, it can lead to infinite loops. For example, imagine a program that defines a function like this. Call this function again. If there's no rule to stop it after a certain point, the program will run forever, caught in its own self-referential trap. This mirrors the logical loops we see in language-based self-referential statements. Self-reference also appears in art and literature. A classic example is the Drawing Hands by M.C. Escher, where two hands are shown drawing each other. Each hand is the creator and the created, forming a loop of causation. In literature, stories sometimes refer to themselves, breaking the fourth wall. For instance, a character might say, "I'm just a character in a story." This moment of self-reference can surprise readers, making them think about the nature of fiction and reality. Beyond their intellectual appeal, self-referential statements can have practical consequences. In law, self-referential rules can create conflicts. For instance, consider a law that says, "This law is not subject to amendment." If lawmakers later decide to amend it, does the amendment take precedence, or does the original rule remain in effect? Legal systems must navigate such questions carefully to avoid contradictions. In technology, self-referential loops can cause problems when they lead to infinite processes. For example, a poorly designed algorithm might repeatedly refer to its previous output without reaching a conclusion. This can crash systems or consume resources unnecessarily. Programmers must design systems with safeguards to prevent such loops. Philosophically, self-referential statements challenge our understanding of fundamental concepts like truth, meaning, and logic. They show that our intuitive ideas about these concepts are not always reliable. For example, we often assume that every statement is either true or false. But self-referential paradoxes like "this statement is false" defy this binary framework. They suggest that truth might be more complex or context-dependent than we think. Some philosophers argue that self-referential paradoxes reveal flaws in traditional logic. They propose alternative systems, such as paraconsistent logic, which allows for contradictions without collapsing into incoherence. Others see self-reference as a natural and unavoidable feature of language and thought. They study it not as a problem to be fixed, but as a phenomenon to be understood. Self-reference also plays a role in understanding consciousness and identity. When you think about yourself thinking, you engage in a form of self-reference. This ability to reflect on one's own thoughts is a defining feature of human consciousness. It's what allows us to ask questions like, "Who am I?" Or, "Why do I believe what I believe?" Self-reference, in this sense, is not just a logical or linguistic phenomenon. It's a core aspect of what it means to be human. Even in everyday life, we encounter self-referential situations. For instance, someone might say, "I always lie." If you take them at their word, then they must be lying about always lying, which means they sometimes tell the truth. But if they're lying in this instance, then their claim about always lying is false. The ambiguity here can be playful or frustrating, depending on how you approach it. It's a reminder that language is not always straightforward, and that self-reference can add layers of complexity. Self-referential statements also appear in humor. Consider the joke, "I'm very humble and I'm proud of it." The humor comes from the self-contradiction, a claim of humility paired with pride in that humility. This playful use of self-reference highlights the ways it can entertain and provoke thought, even outside formal logic or philosophy. In summary, self-referential statements are a fascinating and multifaceted phenomenon. They range from simple observations like, "This statement is written in English," to complex paradoxes like, "This statement is false." They appear in language, mathematics, computer science, art, and everyday life, challenging our assumptions and encouraging us to think more deeply. Whether they create contradictions, infinite loops, or moments of insight, they remind us that the act of turning inward to examine ourselves or our systems can be as illuminating as it is perplexing. Understanding self-reference is not just an intellectual exercise, it's a way to explore the boundaries of meaning, logic, and self-awareness. The paradox of material implication is a puzzle in classical logic that highlights how formal reasoning can lead to conclusions that feel counterintuitive. It arises from the way classical logic defines implication, which is the relationship between two statements where one is said to imply the other. At its core, the paradox challenges our understanding of how statements relate to one another and forces us to reconsider how we interpret logical rules. In classical logic, an implication is represented as if P then Q, where P is the antecedent, the if part, and Q is the consequent, the then part. For example, if it rains, then the ground will be wet. This statement seems straightforward because it aligns with our everyday understanding of cause and effect. The rain causes the ground to become wet. But in classical logic, the truth of an implication is defined in a way that can lead to surprising results. According to classical logic, an implication is considered false only when the antecedent P is true and the consequent Q is false. In all other cases, the implication is true. This definition means that if P is false, the entire implication is automatically true, regardless of Q. This is where the paradox emerges. It allows statements like, if 1 + 1 = 3, then I am the Queen of England, to be logically true. The reason is that the antecedent, 1 + 1 = 3, is false, so the implication as a whole is considered true, no matter how absurd the consequent might be. This result feels counterintuitive because it clashes with our everyday understanding of if-then statements. In ordinary language, we think of implication as suggesting a meaningful connection between the antecedent and the consequent. For example, if it rains, then the ground will be wet makes sense because there is a causal relationship between rain and wet ground. But in classical logic, the truth of an implication depends only on the truth values of P and Q, not on any real-world connection between them. This abstraction is what leads to the paradox. To see why this happens, consider the truth table for implication in classical logic. If P is true and Q is true, if P then Q is true. If P is true and Q is false, if P then Q is false. If P is false, if P then Q is true, regardless of Q. The third row of the table is where the counterintuitive result occurs. When P is false, the implication is always true, even if Q has no logical or causal connection to P. This is why a statement like, if 1 + 1 = 3, then pigs can fly, is considered true in classical logic. The falsehood of the antecedent makes the implication true by definition, which feels strange when compared to how we typically use language. The paradox of material implication is not just an odd quirk of logic. It reveals important differences between formal reasoning and natural language. In everyday conversation, we often expect implications to convey meaningful relationships. When someone says, if you study hard, you'll pass the test, we interpret it as a causal suggestion. Studying hard increases the likelihood of passing. Classical logic, however, strips away these nuances and focuses purely on abstract truth values. This disconnect between formal logic and natural language is a central feature of the paradox. Philosophers and logicians have proposed various ways to address the paradox. One approach is to develop alternative systems of logic that better align with our intuitions. For example, relevance logic introduces the requirement that the antecedent and consequent of an implication must be meaningfully related. In relevance logic, statements like, if 1 + 1 = 3, then I am the Queen of England, would not be valid because there is no connection between the antecedent and the consequent. While this approach resolves the paradox, it also complicates the formal structure of logic, making it less universally applicable. Another approach is to reinterpret how we think about implications in classical logic. Some philosophers argue that the paradox is not a problem with logic itself, but with our expectations. Classical logic is not trying to capture the nuances of natural language. It is a formal system designed to work with abstract truth values. From this perspective, the paradox of material implication is a feature of the system, not a flaw. It reminds us that formal logic operates under rules that may not always align with our everyday reasoning. The paradox also has practical implications for fields like mathematics, computer science, and philosophy. In mathematics, implication is used to prove theorems and establish relationships between statements. Understanding the definition of implication in classical logic is essential for working within these formal systems. In computer science, logical operators are fundamental to programming and algorithms, and the behavior of implication affects how systems process conditional statements. Beyond its technical applications, the paradox has broader philosophical significance. It raises questions about the nature of truth, meaning, and reasoning. What does it mean for one statement to imply another? Is implication a purely formal relationship, or does it require a deeper connection between ideas? The paradox encourages us to think critically about how we use language and logic to understand the world. The paradox of material implication also highlights the importance of context. In natural language, the meaning of an implication often depends on the context in which it is used. For example, if you water the plants, they will grow, assumes a causal relationship based on our knowledge of plants and water. Classical logic, by contrast, removes context and focuses solely on abstract truth values. This abstraction makes logic powerful and versatile, but also creates situations where the results seem counterintuitive. Despite its challenges, the paradox of material implication is a valuable tool for exploring the limits of reasoning and the differences between formal systems and human intuition. It forces us to confront the gap between how we think about implications in everyday life and how they are defined in logic. By examining this gap, we gain a deeper understanding of the strengths and limitations of formal reasoning. In summary, the paradox of material implication reveals the counterintuitive nature of how classical logic defines implication. It allows statements with false antecedents to be true, even when the consequent has no meaningful connection to the antecedent. While this result may feel strange, it highlights the abstract nature of formal logic and its differences from natural language. The paradox challenges our assumptions about implication, truth, and reasoning, encouraging us to think critically about the tools we use to make sense of the world. Through its exploration, we gain insight into the power and complexity of logic, as well as its relationship to human understanding. Circular reasoning, also known by its Latin name Petitio Principii, which means assuming the initial point, is a logical fallacy in which the conclusion of an argument is used as a premise to support itself. In simpler terms, it occurs when someone tries to prove a claim by using the claim itself as evidence. This type of reasoning is problematic because it does not provide any independent support for the argument, creating a loop that lacks meaningful substance. To understand circular reasoning, consider a straightforward example. The Bible is true because it says so in the Bible. This argument assumes the conclusion, the Bible is true, as a premise without offering external evidence or justification. By relying on the very thing it is trying to prove, the argument circles back on itself, failing to provide a convincing or logically valid foundation. The key issue with circular reasoning is that it does not advance knowledge or understanding. Instead of moving from one established fact to another, it relies on repetition of the same claim. For an argument to be persuasive and logical, the premises must provide independent support for the conclusion. Circular reasoning bypasses this requirement, making it a fallacy. To see why this is a problem, imagine someone arguing, "We know democracy is the best system of government because democratic countries are the best." This reasoning assumes the conclusion that democracy is the best, without explaining why or offering evidence beyond the conclusion itself. It creates a closed loop that does not address the question or persuade a critical thinker. Circular reasoning can be subtle, and it often appears in everyday conversations, debates, and even academic discussions. People may not realize they are using circular reasoning because it can feel intuitive or self-evident. For example, someone might argue, "I'm trustworthy because I always tell the truth." While the claim seems reasonable at first glance, it assumes what it sets out to prove, that the person is trustworthy, without offering external evidence to support that trustworthiness. Another common example involves appeals to authority. Suppose someone says, "This scientific theory is correct because the experts say it is." While experts can provide valuable insights, relying solely on their authority without explaining the evidence or reasoning behind the theory can create a circular argument. The premise, "The experts say it's correct," simply assumes the conclusion, "The theory is correct." without providing a clear connection between the two. Circular reasoning is often linked to questions of belief and ideology. For instance, religious or philosophical arguments sometimes fall into circular patterns. A believer might say, God exists because the scriptures say so, and the scriptures are true because they are the word of God. This argument assumes the truth of both the scriptures and God's existence without providing evidence independent of those claims. While such reasoning may feel compelling to those who already accept the premises, it fails to persuade someone who does not share the same initial beliefs. The fallacy of circular reasoning is particularly problematic in science and critical thinking, where the goal is to build arguments based on evidence and logical connections. Scientific reasoning relies on forming hypotheses, testing them through observation and experimentation, and drawing conclusions based on the results. Circular reasoning short-circuits this process by assuming the conclusion rather than demonstrating it. One famous historical example of circular reasoning comes from the 17th century philosopher René Descartes. In his search for certainty, Descartes argued, "I think, therefore I am." He then used the certainty of his own existence to prove the existence of a benevolent God, who in turn guaranteed the reliability of human reason. Critics pointed out that Descartes' reasoning relied on the assumption that his reasoning was already trustworthy, creating a circular structure that some found unconvincing. Despite its flaws, circular reasoning is not always obvious. It can be hidden within complex arguments or disguised by rhetorical flourishes. For example, political debates often include statements like, "This policy is the best choice because it produces the best results." Such claims may sound reasonable, but they rely on the assumption that the results are already agreed upon as the best, without explaining why or how they are superior. To avoid circular reasoning, it is important to critically examine the premises of an argument and ensure they provide independent support for the conclusion. One useful strategy is to ask, does this premise rely on the conclusion being true? If the answer is yes, the argument may be circular. Breaking the loop requires introducing evidence, examples, or reasoning that stands on its own and leads logically to the conclusion. In some cases, circular reasoning is used deliberately, often as a rhetorical tactic. Advertisers, for example, might use circular slogans like, "It's the best because it's number one." Such statements rely on repetition and emotional appeal rather than logical persuasion. While these tactics can be effective in influencing people, they do not hold up to critical scrutiny. Circular reasoning also appears in legal and ethical arguments. For instance, a lawyer might argue, "This action is illegal because the law prohibits it." While true, this statement does not explain why the action is illegal or justify the law itself. Similarly, ethical debates sometimes involve circular arguments, such as lying is wrong because it is unethical. These statements fail to provide a deeper justification for the claim, leaving the argument unconvincing. The problem with circular reasoning is not just that it is logically flawed, it also undermines meaningful dialogue and inquiry. When arguments rely on circular reasoning, they do not provide new information or help resolve disagreements. Instead, they create an echo chamber where the same ideas are repeated without examination. This can lead to polarization, dogmatism, and a lack of progress in understanding complex issues. Despite its shortcomings, recognizing and addressing circular reasoning is an important skill in critical thinking. By identifying circular arguments, we can refine our reasoning, improve the quality of debates, and build stronger, more persuasive arguments. Circular reasoning reminds us that logic is not just about repeating what we already believe. It is about finding connections and evidence that lead to genuine understanding. In summary, circular reasoning is a logical fallacy that occurs when an argument assumes its conclusion as a premise, creating a closed loop that lacks independent support. It is a common and often subtle mistake that can appear in everyday conversations, philosophical debates, and even scientific discussions. While it may seem intuitive, circular reasoning fails to provide meaningful evidence or advance knowledge. By identifying and avoiding circular arguments, we can engage in clearer, more productive reasoning and build stronger foundations for our beliefs and decisions. The term catch-22 refers to a paradoxical situation where a person cannot avoid a problem because the rules governing the situation are inherently contradictory. Popularized by Joseph Heller's 1961 novel of the same name, catch-22 has come to symbolize the frustrating and often absurd predicaments caused by circular logic, bureaucratic rules, or conflicting requirements. At its heart, a catch-22 creates a no-win scenario where any attempt to resolve the problem reinforces the very conditions that make it unsolvable. In the novel Catch-22, Heller tells the story of Captain John Yossarian, a U.S. Army Air Force bombardier during World War II. Yossarian and his fellow airmen face the constant danger of flying combat missions, and many want to avoid these life-threatening assignments. According to military regulations, a pilot can be grounded if they are declared insane. However, there's a catch. Anyone who applies to be grounded due to insanity is demonstrating a rational concern for their safety, which proves they are sane. On the other hand, if a pilot willingly continues to fly dangerous missions, they are considered insane but will not request to be grounded. This circular logic traps the airmen. No matter what they do, they cannot escape their predicament. The brilliance of Catch-22 lies in its ability to capture the absurdity of such situations. The paradox resonates with readers because it mirrors real-life experiences where rules or systems seem designed to work against those caught within them. A Catch-22 creates a closed loop that prevents resolution, leaving individuals feeling powerless and frustrated. Consider a common example in the modern workplace. Suppose you're applying for a job, and the position requires prior experience in a similar role. However, you cannot gain that experience unless you are hired for such a role. This creates a catch-22. You need experience to get the job, but you need the job to gain experience. The requirements reinforce each other, making it nearly impossible to break into the field. Another example of a catch-22 occurs in bureaucracy. Imagine trying to obtain a permit to fix a problem with your property, but you're told you cannot get the permit until the problem is resolved. However, resolving the problem requires the permit. This type of circular regulation is a hallmark of bureaucratic systems, where rigid rules and procedures often create barriers instead of solutions. Catch-22 situations also appear in social dynamics. For instance, someone might want to make new friends but struggles with social anxiety. They avoid social situations because they are anxious, but their isolation makes their anxiety worse, creating a self-perpetuating loop. Similarly, in relationships, people may find themselves caught in patterns where their actions and assumptions reinforce the very issues they are trying to resolve. One of the most striking features of a catch-22 is its inherent unfairness. The rules or conditions often appear logical or reasonable on the surface, but when applied, they create a trap. This unfairness is part of what makes catch-22 scenarios so frustrating. They seem designed to maintain the status quo or protect the interests of those in power while leaving those affected with no way out. The phrase catch-22 has become a cultural shorthand for these types of predicaments, extending far beyond its literary origins. It is often used to describe situations in politics, law, or economics where systemic contradictions make progress impossible. For example, in debates about poverty, people often point out that low-income individuals may face a catch-22 when trying to improve their circumstances. They might need additional education to qualify for better-paying jobs, but they cannot afford the time or money required to pursue that education because they are working long hours to survive. The paradox also applies to global issues, such as climate change. Governments and corporations may argue that economic growth is necessary to fund green initiatives, but unchecked growth often exacerbates environmental damage, making the problem worse. This creates a catch-22 where the proposed solutions contribute to the very problem they aim to solve. One reason the concept of catch-22 resonates so deeply is its connection to the human experience of powerlessness. The rules in a catch-22 are often arbitrary, irrational, or opaque, yet they are enforced with authority. This creates a sense of futility, as individuals feel trapped by forces beyond their control. In Catch-22, Heller uses humor and satire to emphasize the absurdity of these situations, but the underlying themes of frustration and helplessness are universally relatable. Despite its bleak implications, the concept of catch-22 also invites reflection on how we navigate such situations. While a catch-22 may seem inescapable, people often find creative ways to challenge or subvert the system. For instance, Yossarian's approach to the paradox is not to solve it, but to refuse to play by its rules. By prioritizing his survival over the absurd demands of military bureaucracy, he highlights an alternative way of thinking, rejecting the system altogether. This rebellious attitude is not always practical or possible, but it serves as a reminder that sometimes the best response to an impossible situation is to question its very framework. Catch-22 situations also prompt us to examine the systems and structures that create them. Many of these predicaments arise from rigid rules, inflexible policies, or a lack of empathy in decision-making. By identifying the root causes of a catch-22, we can work to design systems that are more humane and adaptable. For example, some organizations have addressed the experience paradox in hiring by offering internships or entry-level roles that provide the experience candidates need to advance. Similarly, programs that combine education and work opportunities can help break the cycle of poverty. In some cases, catch-22 scenarios highlight deeper philosophical questions about the nature of choice and freedom. Are we truly free to make decisions when our options are constrained by contradictory rules? How do we navigate situations where every choice leads to an undesirable outcome? These questions remind us that life is often more complex and paradoxical than it seems, requiring us to balance logic, creativity, and resilience. In conclusion, catch-22 is more than just a literary concept. It is a powerful metaphor for the absurd and contradictory situations we encounter in life. Whether in bureaucracy, social systems, or personal dilemmas, a catch-22 traps individuals in a loop where the conditions for resolving the problem are impossible to meet. By exploring these paradoxes, we gain insight into the flaws in our systems and the ways they can be challenged or reimagined. While a catch-22 may seem inescapable, understanding its dynamics can help us find paths forward, even in the most frustrating and illogical of circumstances. Through its timeless relevance, the concept of catch-22 reminds us to question authority, think critically, and find creative ways to navigate the paradoxes of life. The Cretan liar paradox, also known as the Epimenides paradox, is an ancient and thought-provoking puzzle that challenges our understanding of truth, self-reference, and contradiction. It originated with the philosopher and poet Epimenides of Crete, who is credited with the statement, "All Cretans are liars." On the surface, it seems straightforward, but when you examine the logic behind it, the statement creates a paradox that has intrigued philosophers for centuries. To understand the paradox, let's analyze the statement. Epimenides, a Cretan himself, declares that all Cretans are liars. If his statement is true, then as a Cretan he must be lying. But if he is lying, then his statement cannot be true, meaning that not all Cretans are liars. However, if not all Cretans are liars, his statement is false, which implies that he is telling the truth about lying. This creates an endless loop of contradiction where the statement cannot consistently be classified as either true or false. The paradox hinges on self-reference and the concept of truth. The statement, "All Cretans are liars," refers to the truthfulness of Cretans as a group, but because Epimenides is a member of that group, his own truthfulness is included in the scope of the statement. This creates a situation where the statement undermines itself, making it impossible to resolve without contradiction. The Cretan liar paradox is a specific example of a broader category of self-referential puzzles known as liar paradoxes. These paradoxes arise when a statement refers to its own truth in a way that leads to logical inconsistency. A classic example is the statement, "This statement is false." If the statement is true, then it must be false as it claims, but if it is false, then it must be true, creating the same kind of logical loop. In the case of the Cretan liar paradox, the problem is slightly more complex because it involves a generalization about a group rather than a single self-referential statement. This added layer of complexity has made it a subject of interest in both philosophy and logic, as it raises questions about how we understand truth and generalization in language. One way to approach the paradox is to examine the assumptions behind the statement. For instance, what does it mean to say that all Cretans are liars? Does it imply that every single statement made by a Cretan is false? If so, then the paradox holds, because Epimenides' statement would be self-contradictory. However, if the statement allows for exceptions, if, for example, Cretans lie most of the time but not always, then the paradox dissolves. In this interpretation, Epimenides could be one of the exceptions, making his statement truthful and avoiding the contradiction. Another way to address the paradox is through the concept of levels of language, as proposed by the philosopher Alfred Tarski. Tarski argued that problems like the liar paradox arise because they blur the distinction between a language and a meta-language. A statement like, "This statement is false," operates within the same level of language it is describing, creating a loop. To resolve this, Tarski suggested that we separate the language used to make statements, the object language, from the language used to discuss their truth, the meta-language. Applying this idea to the Cretan liar paradox, we might interpret Epimenides' statement as a claim in a meta-language, which avoids the self-referential loop and allows for a consistent analysis. The paradox also raises questions about the nature of lying and truth. To call someone a liar typically means they habitually tell falsehoods, but it does not mean that every statement they make is false. For example, even a known liar might truthfully say, "It is raining outside," if it happens to be true. This nuance complicates the interpretation of all Cretans are liars. If Epimenides meant that Cretans lie often but not always, then his statement could be seen as hyperbolic rather than paradoxical. However, if we take his claim literally, the paradox emerges in full force. The Cretan liar paradox has significant implications for philosophy, particularly in the study of language, logic, and epistemology. It highlights the challenges of self-reference and the difficulties of defining truth in absolute terms. The paradox also connects to broader philosophical debates about the limits of language and the potential for contradictions within systems of reasoning. In mathematics and logic, the paradox has influenced the development of formal systems that attempt to address self-reference and inconsistency. Kurt Gödel's incompleteness theorems, for example, use a form of self-reference to show that any sufficiently complex mathematical system contains statements that are true but cannot be proven within the system. Similarly, the work of Alfred Tarski and other logicians has sought to formalize the concept of truth in ways that avoid the pitfalls of self-referential paradoxes. The paradox also has cultural and literary significance. It serves as a metaphor for situations where statements or systems undermine themselves, creating contradictions that defy resolution. For example, political or ethical debates often involve arguments that, like the Cretan liar paradox, turn back on themselves and challenge our assumptions about consistency and truth. Despite its ancient origins, the Cretan liar paradox remains relevant today. It invites us to think critically about the language we use and the assumptions we make about truth and communication. By exploring the paradox, we gain insight into the complexities of reasoning and the ways in which self-reference can lead to unexpected challenges. In summary, the Cretan liar paradox is a timeless puzzle that exposes the difficulties of self-reference and the challenges of defining truth. It illustrates how simple statements can lead to profound contradictions, forcing us to question our assumptions and refine our understanding of logic and language. Through its exploration, we are reminded of the power of critical thinking and the enduring mysteries of human reasoning. The infinite regress problem is a philosophical issue that arises whenever a chain of reasoning, explanation, or justification requires an endless sequence of prior steps. At its core, the problem highlights a fundamental question. If every answer or explanation depends on something before it, how do we ever reach a solid foundation? Infinite regress exposes the challenge of finding a stopping point, an ultimate explanation or principle that doesn't depend on anything else. It is a recurring issue in many areas of philosophy, including metaphysics, epistemology, ethics, and theology. To understand the problem, imagine asking a series of why questions. For example, consider the claim, "The sky is blue." You might ask, why is the sky blue? The answer could be because light scatters in the atmosphere. Then you ask, why does light scatter in the atmosphere? The response might be, because particles in the air scatter shorter wavelengths of light more effectively than longer wavelengths, and so on. If each answer leads to another question indefinitely without ever reaching a final explanation, you have an infinite regress. The issue becomes problematic when the regress prevents meaningful understanding or resolution. In some cases, infinite regress is merely an intellectual curiosity, a sign that more questions can always be asked. But in other cases, it threatens the coherence of an argument or the viability of a theory. If every claim depends on something else without end, the entire chain may collapse, leaving no foundation to support it. One of the most well-known examples of the infinite regress problem occurs in the study of justification in epistemology, the branch of philosophy that explores knowledge and belief. Suppose someone claims to know a fact, say the Earth orbits the Sun. When asked how they know this, they might reply, because scientists have observed it. If pressed further, they might say, because scientific observation relies on evidence and reasoning. But how do we justify the reliability of evidence and reasoning? If every justification requires another justification, the process never ends. Without a stopping point, it's unclear how any belief can be fully justified. To address the infinite regress problem in epistemology, philosophers have proposed several strategies. One approach is foundationalism, which asserts that some beliefs are basic or self-evident and do not require further justification. These basic beliefs serve as the foundation upon which other beliefs are built. For example, sensory perceptions like "I see a tree" or logical principles like A equals A might be considered foundational. Foundationalism provides a stopping point to avoid infinite regress, but it raises questions about how to identify these basic beliefs and whether they truly require no justification. Another approach is coherentism, which rejects the idea of foundational beliefs and instead views justification as a matter of coherence within a system of beliefs. In this view, beliefs are justified not because they rest on a foundation, but because they fit together in a consistent and mutually supporting network. For example, the belief that the Earth orbits the Sun is justified because it coheres with other beliefs about gravity, astronomy, and physics. While coherentism avoids the problem of infinite regress, critics argue that it risks circularity, as the justification for each belief depends on the others within the system. A third approach is infinitism, which embraces the idea of an infinite chain of justification. Infinitists argue that infinite regress is not a problem as long as the chain remains logically sound and provides increasingly detailed explanations. For example, in science, one explanation often leads to deeper questions, which lead to further explanations. Infinitists see this as a natural and productive process rather than a failure of justification. However, this view raises practical concerns, as it may be impossible to access or comprehend an infinite sequence of reasons. The infinite regress problem also appears in metaphysics, particularly in discussions about causation. Consider the question, what caused the universe to exist? If we say the universe was caused by something else, say the Big Bang, then we can ask, what caused the Big Bang? If that cause also requires a cause, the chain of causation stretches infinitely backward. Without a first cause or an ultimate explanation, it's difficult to make sense of the existence of the universe. In response to this issue, some philosophers and theologians have proposed the idea of a first cause or unmoved mover, a cause that itself is not caused by anything else. This concept is central to cosmological arguments for the existence of God, such as those advanced by Thomas Aquinas. According to this view, the chain of causation must terminate in a being or principle that exists necessarily and provides the ultimate explanation for everything else. Critics, however, question whether the notion of a first cause is coherent or whether it simply shifts the problem. Why does the first cause exist? The problem also arises in ethics, where it affects how we justify moral principles. For example, consider the claim, lying is wrong. If asked why lying is wrong, someone might respond, because it causes harm. But why is causing harm wrong? If each moral claim requires a deeper justification, the chain of reasoning could extend infinitely. To avoid this regress, some ethicists appeal to foundational principles, such as utilitarianism's focus on maximizing happiness, or Kantian ethics' emphasis on duty and universalizability. Others argue that ethical reasoning is a matter of coherence, similar to coherentism in epistemology. The infinite regress problem even shows up in everyday life, often in the form of children's endless why questions. A child might ask, "Why do we eat food?" The parent might answer, "Because our bodies need energy." The child then asks, "Why do our bodies need energy?" And the conversation spirals into a never-ending sequence of explanations. While this can be an innocent exercise in curiosity, it mirrors the deeper philosophical problem of finding ultimate answers. Interestingly, not all infinite regresses are problematic. In mathematics, for example, infinite sequences and series are well understood and can lead to meaningful results. For instance, the sum of the infinite series converges to 2. In this context, infinity is not a barrier but a tool for understanding and calculation. The distinction between benign and problematic infinite regresses depends on whether the regress provides meaningful insight or whether it obstructs understanding. In conclusion, the infinite regress problem is a profound and enduring challenge in philosophy that cuts across multiple disciplines. It forces us to confront the limits of explanation, justification, and causation, highlighting the difficulties of finding ultimate answers. While foundationalism, coherentism, and infinitism offer different strategies for addressing the problem, none is without its critics. The problem reminds us that our understanding of the world often rests on assumptions, interpretations, or frameworks that we may never fully resolve. By grappling with the infinite regress problem, we deepen our appreciation for the complexity of reasoning and the mysteries that continue to inspire philosophical inquiry. The Dichotomy Paradox, one of Zeno of Elea's most famous philosophical puzzles, is a profound exploration of motion, infinity, and the nature of division. It is part of a series of paradoxes Zeno proposed to challenge the intuitive understanding of motion and support the philosophical teachings of Parmenides, who argued that change and motion are illusions. While the paradox appears straightforward at first glance, its implications stretch across mathematics, physics, and philosophy, raising questions that remain relevant and thought-provoking even today. The paradox begins with a simple scenario. Imagine a person attempting to walk from one point A to another point B. To reach B, the person must first cover half the distance between A and B. Let's call this halfway point C. After reaching C, the person must then cover half the remaining distance to B, and then half of what remains after that, and so on. Each step divides the remaining distance into smaller and smaller segments, creating an infinite sequence of steps that the person must complete to reach B. Here lies the paradox. If the journey requires completing an infinite number of steps, how can the person ever reach B? Each step, no matter how small, takes some amount of time to complete. Intuitively, completing an infinite sequence of steps would seem to require an infinite amount of time, making the destination unreachable. Yet, in everyday life, people do walk from one place to another, and motion clearly occurs. The dichotomy paradox creates a tension between the apparent impossibility of completing infinite tasks and the undeniable reality of motion. The mathematical resolution demonstrates that an infinite number of steps does not necessarily require an infinite amount of time or distance. This is because the time required for each successive step also decreases, just as the distance does. For example, if the person takes half a second to complete the first step, a quarter of a second for the second step, and so on, the total time to complete all the steps converges to a finite value. The paradox is resolved mathematically, but its deeper implications extend far beyond the realm of numbers. Philosophically, the dichotomy paradox raises questions about the nature of motion. How does something move if it must complete an infinite sequence of steps? Does motion occur continuously as a smooth and uninterrupted flow, or is it composed of discrete moments, like frames in a film? These questions touch on fundamental debates about whether space and time are continuous or discrete, a topic that remains unresolved in modern physics. Classical physics, as described by Isaac Newton, treats motion as continuous, meaning that there are no smallest units of space or time. In this framework, the paradox is resolved by recognizing that time and distance can both be divided infinitely without preventing motion. However, modern physics complicates this picture. In quantum mechanics, space and time may not be infinitely divisible. At extremely small scales, phenomena like the Planck length and Planck time represent fundamental limits beyond which our current understanding of physics breaks down. If space and time are discrete at these scales, the dichotomy paradox might take on new meaning, as it would suggest a natural stopping point for the infinite division of motion. Beyond its implications for motion in physics, the dichotomy paradox also highlights the limitations of human intuition. Intuitively, the idea of completing an infinite sequence of steps feels impossible, as our minds struggle to grasp the concept of infinity. Yet mathematics shows that this is not only possible, but inevitable under certain conditions. This gap between intuition and formal reasoning challenges us to think more critically about the assumptions we make and the tools we use to understand the world. The paradox has practical implications for how we think about processes and tasks in everyday life. Many activities can be broken down into smaller and smaller steps, whether it's solving a problem, completing a project, or learning a new skill. At first, the sheer number of steps involved might seem overwhelming, but the dichotomy paradox reminds us that progress is possible, even when the process seems infinite. By focusing on completing each step, no matter how small, we can move closer to our goals. In a broader sense, the dichotomy paradox invites reflection on the nature of infinity itself. Infinity is not just a mathematical abstraction, it is a concept that shapes how we think about the universe, from the vastness of space to the limits of human knowledge. By exploring the paradox, we gain a deeper appreciation for the complexities of reasoning about the infinite and the finite simultaneously. The dichotomy paradox also connects to other fields, such as computer science and engineering. For example, algorithms often involve iterative processes, where a task is repeated with progressively smaller steps. Understanding how infinite sequences converge to finite results is essential for designing efficient algorithms and solving complex problems. Similarly, in digital graphics, the concept of infinite division is used to create smooth curves and realistic images by breaking shapes into smaller and smaller parts. Despite its mathematical resolution, the dichotomy paradox continues to inspire philosophical inquiry. It forces us to grapple with questions about the nature of reality, the structure of time and space, and the relationship between the infinite and the finite. It challenges us to reconcile the abstract world of mathematics with the concrete experiences of everyday life, reminding us that even simple scenarios can reveal profound truths. In summary, the dichotomy paradox is a timeless puzzle that uses the concept of infinite division to challenge our understanding of motion, infinity, and reasoning. While modern mathematics resolves the paradox through the concept of limits, its philosophical implications continue to provoke deep questions about the nature of reality and the human mind. By exploring the paradox, we gain insight into the power of critical thinking and the interplay between logic, intuition, and the physical world. The dichotomy paradox remains a source of fascination, demonstrating that even the simplest ideas can lead to profound and far-reaching insights. Turing's halting problem is a fascinating and important concept in computer science and mathematics. It shows that there are some questions that no computer program can ever solve, no matter how advanced the computer is or how much time it has. This problem was first introduced by Alan Turing in 1936, and it changed how we think about what computers can and cannot do. At its core, the halting problem is about understanding the limits of computation. The halting problem starts with a simple question. Imagine you have a computer program, and you give it some input to work with. Will the program eventually finish running, or halt, or will it keep running forever? This might seem like a problem a computer should be able to solve. After all, computers are designed to analyze and process data. So why couldn't one figure out whether another program will stop or not? Let's think about this more concretely. Imagine a program you want to analyze, and we'll call it P. This program is given a specific input, which we'll call I. You might ask another program, a halting checker, to look at P and I and figure out if P will halt when it processes I. If P eventually stops, the halting checker will tell you, yes, it halts. If P will run forever, the checker will say, no, it doesn't halt. It seems reasonable to believe that such a program could exist, but Alan Turing proved that this is impossible. He showed that no program, no matter how it's written, can always determine whether another program will halt. His proof is both simple and ingenious, and it uses a clever twist to create a logical contradiction. Here's how the proof works. Let's assume, just for argument's sake, that a perfect halting checker does exist. We'll call it H. The program H is supposed to be able to analyze any program P and its input I and correctly predict whether P will halt or not. Now Turing asks us to imagine another program, which we'll call T, that uses H in a very tricky way. The program T works like this. It takes a program, let's call it Q, as its input. T then asks H to predict whether Q will halt when it is given itself Q as its input. If H predicts that Q of Q will halt, T does something unexpected. It enters an infinite loop and doesn't halt. On the other hand, if H predicts that Q of Q will not halt, T immediately halts. Now we ask the big question, what happens when we give T itself as input? That is, what happens when T tries to analyze T of T? This is where things get interesting. If H predicts that T of T will halt, then T will enter an infinite loop and never halt, contradicting H's prediction. On the other hand, if H predicts that T of T will not halt, then T will halt, again contradicting H's prediction. Either way, H's prediction is wrong, and this contradiction proves that no perfect halting checker can exist. This result is shocking because it means there are limits to what computers can do. Even in theory, it's impossible to design a program that can always predict whether another program will stop. This limitation isn't about the speed or power of a computer. It's a fundamental property of computation itself. The halting problem is more than just an abstract puzzle. It has real-world implications. In computer science, many tasks involve predicting the behavior of programs. For example, software developers might want to know if a program has a bug that causes it to run forever, or if it will eventually finish its task. Tools like code analyzers and debuggers can help in many cases, but the halting problem proves that no tool can handle every situation. There will always be some cases where it's impossible to know for sure. The problem also shows up in other areas of computer science, like artificial intelligence. AI systems sometimes need to analyze their own behavior or predict the behavior of other systems. The halting problem reminds us that there are limits to how much machines can understand or predict, especially when self-reference is involved. This is why building AI systems that are fully self-aware or perfectly predictable is such a difficult challenge. The halting problem also raises deeper philosophical questions about knowledge and reasoning. It challenges the idea that every question has an answer, or that we can fully understand complex systems. In a way, it's a humbling reminder that there are boundaries to human and machine understanding. No matter how advanced our technology becomes, there will always be mysteries that we cannot fully solve. Turing's work on the halting problem also helped lay the foundation for modern computing. In his research, Turing introduced the idea of the Turing machine, a simple but powerful mathematical model of a computer. The Turing machine can simulate any algorithm, making it a key concept in computer science. By showing that even a Turing machine cannot solve the halting problem, Turing demonstrated the inherent limitations of computation. Despite these limitations, the halting problem has practical value. It helps computer scientists understand which problems can be solved and which cannot, allowing them to focus on what is achievable. For example, when designing tools for detecting bugs or optimizing programs, engineers can create systems that work for specific cases or common patterns, even if they can't solve every possible scenario. The halting problem also highlights the creativity and adaptability of human problem solving. Unlike machines, humans can think outside the box, approach problems from new angles, and find solutions to challenges that seem impossible. While computers are bound by strict rules, humans can use intuition, imagination, and lateral thinking to overcome obstacles. In conclusion, Turing's halting problem is a groundbreaking discovery that reveals the limits of computation. It proves that no program can always predict whether another program will halt, no matter how well it is designed. This insight challenges our assumptions about what computers can do and has profound implications for computer science, artificial intelligence, and our understanding of reasoning and knowledge. Alan Turing's work on the halting problem continues to inspire scientists and philosophers, reminding us of the beauty and complexity of both computation and the human mind. It's a powerful reminder that some questions will always remain unanswered. But that doesn't stop us from exploring and discovering all that we can. Goodman's paradox, also known as the new riddle of induction, is a thought-provoking challenge to our understanding of how we make predictions about the world. Introduced by the philosopher Nelson Goodman in 1955, it builds on the classic problem of induction posed by David Hume, but adds a new layer of complexity. Goodman's paradox forces us to question why some predictions seem logical and reliable, while others, even though they follow the same rules, seem arbitrary or absurd. It's a puzzle that cuts to the heart of how we reason about evidence and make sense of patterns in the world. To understand Goodman's paradox, let's start with the problem of induction. Induction is the process of making generalizations based on specific observations. For example, if you've seen the sun rise every morning for your entire life, you might conclude that the sun will rise again tomorrow. This kind of reasoning feels natural and reliable, and it underpins much of science and everyday life. However, Hume pointed out that induction lacks a logical guarantee. Just because the sun has always risen in the past doesn't mean it necessarily will in the future. There's no logical necessity connecting past observations to future events. Goodman's paradox takes this problem a step further by asking why certain generalizations seem more reasonable than others. He introduces a thought experiment involving a hypothetical property called GRU. An object is defined as GRU if it is observed to be green before a certain time, say the year 2100, but blue afterward. Now consider emeralds. We've observed many emeralds and they've all been green. Based on this, we might conclude that all emeralds are green. But using the concept of GRU, we could just as easily conclude that all emeralds are GRU. According to this reasoning, emeralds will appear green until 2100 and then suddenly turn blue. Here's the paradox. Both the prediction all emeralds are green and the prediction all emeralds are GRU are consistent with the evidence we've observed so far. Both are based on the same set of observations. Yet all emeralds are green feels intuitive and reasonable, while all emeralds are GRU seems bizarre and arbitrary. Goodman's question is, why? What makes some generalizations feel valid and others not, even when they're supported by the same evidence? Goodman's paradox challenges the assumptions we make about how we classify and predict. It reveals that our reasoning about induction depends not just on evidence, but also on the concepts and categories we use. The terms green and GRU are both logically valid, but green aligns with our intuitive and conventional way of describing the world, while GRU does not. Goodman's insight is that there's no purely logical reason to prefer one over the other. The distinction comes from how we use language, form habits, and make sense of our experiences. One way to approach Goodman's paradox is to consider the role of simplicity and convention in our reasoning. The concept of green is simple, familiar, and widely used in describing colors, while GRU is complicated and contrived. This simplicity makes green a more natural and practical choice for generalizing observations. However, Goodman argues that simplicity itself is not an absolute standard. What seems simple to us might be arbitrary from another perspective. In a world where GRU were the standard term, the concept of green might seem strange. Another way to address the paradox is to focus on the predictive success of certain generalizations. Over time, the concept of green has proven to be reliable for making accurate predictions about emeralds and other objects. This success reinforces our trust in green as a meaningful property. In contrast, GRU has no track record of success because it's a fabricated concept designed for the thought experiment. This practical consideration helps explain why we favor some generalizations over others, even if it doesn't fully resolve the paradox. Goodman's paradox also highlights the importance of context and background knowledge in shaping our reasoning. When we observe that emeralds are green, We interpret this observation within a broader framework of scientific understanding, which includes our knowledge of light, color perception, and the properties of materials. This framework supports the concept of green and makes GRU unnecessary. Without this context, it would be harder to justify why one generalization feels more reasonable than the other. The paradox has significant implications for philosophy and science. It challenges the idea that induction is a purely logical process and suggests that our reasoning is shaped by factors like simplicity, convention, and prior experience. This has led to debates about the nature of scientific theories and how they are justified. Some philosophers argue that science progresses by selecting the simplest and most elegant explanations, while others emphasize the role of historical and social factors in shaping scientific practice. Goodman's paradox also has practical implications for fields like artificial intelligence and machine learning. These technologies rely on algorithms to identify patterns and make predictions based on data. The paradox raises questions about how these algorithms decide which patterns to prioritize and whether they can replicate human reasoning about induction. For example, if a machine learning system encounters a dataset that could be explained using GRU instead of green, how does it decide which concept to use? Addressing this question requires not just technical solutions, but also philosophical reflection on the nature of learning and reasoning. In everyday life, Goodman's paradox encourages us to think critically about the assumptions behind our generalizations. When we make predictions or draw conclusions, we often take for granted the categories and concepts we use. The paradox reminds us that these choices are not purely logical. They're shaped by habits, context, and practical considerations. By reflecting on these factors, we can become more aware of the limits and biases in our reasoning. Goodman's paradox also invites us to consider the creative and flexible nature of human thought. While the concept of GRU seems absurd, it highlights how language and imagination can create new ways of classifying the world. This creativity is a double-edged sword. It allows us to explore new ideas and possibilities, but it also challenges us to distinguish meaningful patterns from arbitrary ones. In conclusion, Goodman's paradox is a profound exploration of the nature of induction and the factors that shape our reasoning about evidence and predictions. It shows that induction is not just about observing patterns, but also about choosing the concepts and categories we use to describe them. By challenging our assumptions and highlighting the role of simplicity, convention, and context, Goodman's paradox deepens our understanding of reasoning and its limitations. It remains a central puzzle in philosophy, inspiring ongoing debates about the foundations of science, language, and human thought. Buridan's ass is a philosophical paradox that explores decision-making in situations where two equally appealing options are available, and neither has a clear advantage over the other. This thought experiment illustrates how rationality can sometimes lead to paralysis, even when the situation requires action. It's named after the 14th century French philosopher Jean Buridan, who is often associated with the idea, though he didn't explicitly formulate the paradox in this form. The classic scenario goes like this. Imagine a hungry and thirsty donkey, placed exactly midway between a stack of hay and a bucket of water. Both options are equally necessary for survival and equally appealing. Since there is no reason to choose one over the other, the donkey cannot make a decision. The result is that the donkey starves and dies, unable to resolve the conflict between its options. This paradox raises questions about how we make decisions and whether perfect rationality can sometimes lead to irrational outcomes. It assumes that the donkey is entirely rational and that its choices are based solely on reason. In this case, reason fails the donkey because it cannot find a rational basis for choosing one option over the other. The scenario highlights the limits of decision-making processes that rely solely on logic when faced with equally weighted alternatives. To make this more relatable, consider a person trying to decide between two equally good restaurants for dinner. Each offers the same quality of food, similar prices, and a similar distance from their location. If the person insists on choosing based purely on rational evaluation, they may get stuck in an endless loop of comparison, unable to make a decision. In reality, most people eventually choose one option, often arbitrarily, but the paradox challenges the assumption that reason alone can always lead to action. The paradox has implications for fields beyond philosophy, including economics, psychology, and artificial intelligence. In economics, it underscores the importance of having differentiating factors in consumer choices. When two products are identical in every way, consumers may struggle to decide. Marketers often introduce small, arbitrary distinctions like packaging or branding to help break the tie and encourage decisions. In psychology, the paradox reflects the phenomenon of decision paralysis. People sometimes freeze when faced with too many options or when options are too similar. This can happen in everyday life, such as when choosing between two equally attractive job offers, deciding on a college to attend, or even selecting an outfit to wear. In these cases, the fear of making the wrong choice can lead to hesitation, procrastination, or inaction. In artificial intelligence, Buridan's ass raises challenges in programming decision-making algorithms. An AI system might encounter situations where it cannot prioritize one action over another if both seem equally beneficial. For example, a robot designed to navigate a room might freeze if it encounters two equally efficient paths and cannot break the tie. To prevent this, programmers often introduce randomization or predefined preferences to avoid such deadlocks. The paradox also invites questions about human nature. Are we, like the donkey, capable of getting stuck between two options? The answer lies in how humans differ from purely rational beings. While the donkey in the paradox operates strictly on rationality, humans often rely on other factors like intuition, emotions, or external influences to make decisions. For instance, a person in the restaurant dilemma might flip a coin, choose based on a past experience, or even pick randomly. These methods may not be strictly rational, but they allow decisions to be made and action to follow. To understand this further, let's look at a real-world example. Imagine someone shopping for a new smartphone. They narrow their choices to two models, each offering similar features, performance, and price. They spend hours reading reviews, comparing specifications, and consulting friends, but neither option stands out as better. Days pass, and they still haven't made a purchase. This is a modern version of Buridan's ass, where the inability to choose leads to wasted time and missed opportunities. Eventually, external factors, like a limited-time discount or a recommendation from a trusted friend, might push them to choose one option, but without these influences, they could remain stuck. Another example can be seen in politics. Sometimes voters face two candidates who seem equally qualified or equally flawed. In such cases, deciding whom to vote for can feel impossible. This can lead to voter apathy, where people abstain from voting altogether because they cannot justify choosing one candidate over the other. Here, the inability to decide has real consequences, just as it does for the donkey in the paradox. Buridan's ass also relates to the broader concept of free will. If a decision maker, whether a donkey or a human, cannot choose without a clear reason, does this suggest that free will requires more than just rationality? Some argue that free will involves the ability to act independently of purely logical processes. In other words, humans are capable of making choices that aren't strictly rational, but are driven by other aspects of their personality or experience. This capacity might save us from the paralysis described in the paradox. Critics of the paradox argue that it oversimplifies decision-making by assuming perfect rationality. In reality, most beings, human or animal, don't operate in a purely logical way. A real donkey, for example, might choose the hay or the water based on subtle factors like a slight difference in smell or instinct. Similarly, humans rarely make decisions based solely on reason. Personal preferences, gut feelings, and social influences often play a role, even when the options seem identical. The paradox also assumes a static situation where no external factors intervene. In real life, circumstances often change, forcing decisions to be made. For example, if the donkey in the paradox starts feeling hungrier than it is thirsty, it might choose the hay. Similarly, if one of the two restaurants closes, the diner's choice becomes obvious. These dynamic elements are missing from the original scenario, but they are critical in real-world decision-making. Despite these criticisms, the paradox serves as a valuable thought experiment. It challenges us to think about how we make decisions and what happens when rationality fails. It reminds us that action sometimes requires moving beyond pure logic and embracing other decision-making tools, whether intuition, randomness, or external guidance. In conclusion, Buridan's ass is more than just a story about a donkey. It is a powerful metaphor for the challenges of decision-making and the limits of rationality. While it may not perfectly reflect real-world behavior, it highlights the importance of differentiating factors, the role of intuition, and the need to act even when no clear choice exists. Whether applied to philosophy, economics, psychology, or artificial intelligence, the paradox continues to spark debate and inspire solutions to the age-old problem of indecision. The Grelling-Nelson Paradox is a logical puzzle that arises from self-reference and classification. It explores how we define and categorize words and concepts, and it reveals the unexpected complications that can occur when language refers to itself. This paradox, like many others in logic, shows how something as seemingly simple as describing a word can lead to a contradiction. The paradox is based on the idea of dividing adjectives into two categories, autological and heterological. An adjective is autological if it describes itself. For example, the word short is autological because the word itself is short. Similarly, polysyllabic is autological because it has multiple syllables. On the other hand, an adjective is heterological if it does not describe itself. For instance, the word long is heterological because the word itself is not long, and monosyllabic is heterological because it has more than one syllable. Now comes the twist. What about the word heterological itself? If heterological is heterological, it must not describe itself. But if it does not describe itself, then it must be autological, meaning it does describe itself. This creates a contradiction. No matter how you classify the word heterological, it leads to a logical inconsistency. To make this clearer, let's break it down step by step. First, suppose heterological is heterological. By definition, a heterological word does not describe itself. If heterological is heterological, then it does not describe itself. But if it does not describe itself, that means it must be autological, contradicting the original assumption. Now suppose heterological is autological. If it is autological, then it describes itself. But if it describes itself, that means it cannot be heterological. However, if it is not heterological, it contradicts the very meaning of being heterological, which is not describing itself. Again, we end up with a contradiction. This paradox shows how self-reference can create logical problems that seem impossible to resolve. It's closely related to other self-referential paradoxes, like the liar paradox, this statement is false, and Russell's paradox in set theory. All of these paradoxes involve situations where the act of referring to oneself leads to a loop of contradictions. To understand the Grelling-Nelson paradox, it's helpful to think about how we use language. Words and definitions are tools we use to describe the world, but they are also part of the world they describe. When we try to use language to describe itself, we sometimes run into problems because language wasn't designed to handle these kinds of self-referential situations. It's like trying to measure a ruler with itself. You can do it to some extent, but it's easy to get tangled in contradictions. The paradox also highlights the limits of classification systems. In many cases, we like to divide things into neat categories. Yes or no, true or false, black or white. But the Grelling-Nelson paradox shows that some concepts resist this kind of binary classification. Some words, like heterological, defy easy categorization, and this challenges our assumptions about how language and logic work. Let's consider a more everyday example. Imagine you're organizing books into two piles, books that are self-referential and books that are not. A book that says, "This book is about itself," would go into the self-referential pile. A book that says, "This book is about birds," would go into the non-self-referential pile. Now imagine a book that says, "This book does not belong in the self-referential pile." Where would you put it? If you put it in the self-referential pile, it contradicts its own statement. But if you put it in the non-self-referential pile, it also contradicts its statement. The problem is the same as the Grelling-Nelson paradox. The act of categorization creates a contradiction. The Grelling-Nelson paradox has implications beyond philosophy and logic. It's relevant to fields like mathematics, computer science, and linguistics, where self-reference often plays a role. For example, in programming, self-referential problems can arise when a function calls itself or when a system tries to analyze its own behavior. These situations can lead to infinite loops or other unexpected outcomes, much like the paradox. In mathematics, the paradox is related to Gödel's incompleteness theorems, which show that any sufficiently complex formal system contains statements that are true but cannot be proven within the system. These theorems rely on self-referential constructions, similar to the Grelling-Nelson Paradox, to demonstrate the limits of formal logic. The paradox also raises questions about the nature of meaning and definition. When we define a word, we usually rely on other words to explain it. But what happens when we try to define a word in terms of itself? The Grelling-Nelson Paradox shows that self-referential definitions can lead to contradictions, suggesting that meaning is not as straightforward as it might seem. To resolve the paradox, some philosophers and logicians argue that we need to refine our understanding of language and logic. One approach is to introduce additional rules or distinctions that prevent self-referential contradictions. For example, some systems of logic use a hierarchy of levels, where a word can only refer to things at a lower level and not to itself. This approach, called the theory of types, was developed by Bertrand Russell to address similar paradoxes in set theory. While it can resolve some problems, it also adds complexity to the system and doesn't eliminate all forms of self-reference. Another approach is to embrace the paradox and see it as a feature, not a bug, of language and thought. Some philosophers argue that self-referential paradoxes reveal the limitations of our logical systems and challenge us to think more deeply about how we use language. Rather than trying to eliminate the paradox, they suggest that we should learn to live with it and explore its implications. In everyday life, the Grelling-Nelson Paradox reminds us that not everything can be neatly categorized. Sometimes, ambiguity and contradiction are unavoidable, and that's okay. Whether we're organizing words, books, or ideas, we need to recognize the limits of our systems and be open to complexity. The paradox encourages us to think critically about how we define and classify the world, and it reminds us that even simple concepts can lead to profound questions. In conclusion, the Grelling-Nelson Paradox is a fascinating example of how language and logic can interact in unexpected ways. It challenges our assumptions about meaning, definition, and categorization, and it shows how self-reference can lead to contradictions that defy resolution. Whether we encounter this paradox in philosophy, mathematics, computer science, or everyday life, it serves as a reminder of the complexity of the world and the tools we use to understand it. By exploring these challenges, we can deepen our understanding of language, logic, and the limits of human thought. The Protagoras versus Euathlus paradox is a famous legal and logical puzzle that deals with contracts, obligations, and the limits of reasoning. It involves two individuals, Protagoras, a renowned sophist and teacher of law, and Euathlus, his ambitious student. The paradox arises when a disagreement over payment leads to a legal dispute, creating a loop of arguments where both parties seem justified in claiming victory. This case has fascinated thinkers for centuries, as it raises questions about logic, justice, and the interpretation of agreements. Here's how the story unfolds. Euathlus agrees to study law under Protagoras, but the terms of payment are unusual. Protagoras offers to teach Euathlus without requiring immediate payment. Instead, the agreement states that Euathlus will pay Protagoras for his education after he wins his first court case. This arrangement seems reasonable at first, as it aligns payment with the success of the student. However, a problem arises when Euathlus completes his studies but does not take on any legal cases. Protagoras grows frustrated, feeling that he has fulfilled his part of the bargain and deserves to be paid. When Euathlus refuses to pay, Protagoras takes him to court, leading to the paradox. In court, Protagoras argues that he should win the case no matter what. His reasoning is as follows. If the court rules in his favor, then Euathlus must pay because the court has decided so. If the court rules in Euathlus's favor, then Euathlus will have won his first case, fulfilling the condition of their agreement, and he will still be obligated to pay. Either way, Protagoras believes he is entitled to payment. Euathlus, on the other hand, counters with his own argument, which is equally compelling. He claims that he should not have to pay under any circumstances. If the court rules in his favor, then the court's decision exempts him from payment. If the court rules in Protagoras' favor, then he has still not won a case, so the condition of their agreement has not been met, and he does not owe payment. From Euathlus' perspective, he wins either way. This creates a logical paradox where both sides seem to have irrefutable arguments for why they should prevail. The paradox is rooted in the self-referential nature of the agreement and the interplay between the court's ruling and the conditions of the contract. It's a legal and logical loop where each argument depends on the outcome of the case, making it impossible to resolve without contradiction. To understand this better, let's break down the reasoning on both sides. Protagoras' argument hinges on the idea that the court's ruling overrides the terms of the original agreement. If the court orders Euathlus to pay, then the matter is settled, and Euathlus must comply. Alternatively, if the court rules in Euathlus' favor, Protagoras argues that the agreement's condition is fulfilled, as Euathlus will have won his first case. In either scenario, Protagoras sees himself as entitled to payment. Euathlus' argument, however, focuses on the specific terms of the agreement. He insists that he only owes payment after winning his first case, and he has not done so. If the court rules in his favor, the ruling absolves him of payment. If the court rules against him, he has still not won a case, so the condition of the agreement remains unfulfilled. From his perspective, Protagoras has no claim to payment under any outcome. The paradox illustrates the complexities of legal reasoning and the potential for contracts to create unintended consequences. It challenges the assumption that all agreements can be interpreted in a straightforward manner and highlights how logic can sometimes lead to contradictory outcomes. The case also underscores the importance of clarity in contracts. If the agreement between Protagoras and Euathlus had been more specific about the conditions for payment, the paradox might have been avoided. Beyond its legal implications, the Protagoras versus Euathlus paradox has broader philosophical significance. It touches on the nature of justice, the interpretation of contracts, and the role of intention in agreements. It also raises questions about the limits of logic and the potential for reasoning to lead to deadlocks when applied to self-referential situations. One way to explore this paradox is to consider its relevance in modern contexts. In business, for example, ambiguous contracts can lead to disputes similar to this one. Imagine a company hires a freelancer to complete a project with a payment clause tied to the project's approval by a third party. If the project is completed but never submitted for approval, does the freelancer deserve payment? Situations like this show how the principles of the Protagoras versus Euathlus paradox still apply today. The paradox also appears in broader discussions about fairness and equity. In any dispute, both parties often believe they have a valid claim, and finding a resolution requires balancing competing interests. The legal system is designed to provide clarity, but as this case shows, it can also become entangled in logical loops when the issues are deeply self-referential or ambiguous. One way to resolve the paradox is to move beyond strict logic and consider practical or ethical factors. For example, a court might decide that Protagoras deserves partial payment for his teaching, even if the original agreement's conditions have not been fully met. Alternatively, the court might rule that Euathlus' refusal to take on cases violates the spirit of the agreement, even if it does not technically breach its terms. These approaches involve subjective judgments that go beyond the rigid logic of the paradox, emphasizing fairness over consistency. The Protagoras versus Euathlus paradox also invites reflection on the purpose of education and agreements. Protagoras' teaching was intended to prepare Euathlus for a career in law, and the payment arrangement was designed to reflect the success of that preparation. By refusing to take on cases, Euathlus undermines the intent of the agreement, even if he technically adheres to its terms. This raises questions about the relationship between the letter and spirit of agreements and the obligations of both parties in a contract. In conclusion, the Protagoras versus Euathlus paradox is a timeless puzzle that continues to provoke thought and debate. It reveals the complexities of contracts, the challenges of legal reasoning, and the potential for logic to lead to contradictions. By examining this paradox, we gain insight into the nature of justice, the interpretation of agreements, and the limits of human reasoning. Whether viewed as a philosophical thought experiment, a lesson in legal theory, or a reflection on human behavior, it remains a fascinating example of how simple situations can lead to profound questions. This paradox often arises in theological and philosophical discussions about the nature of an omnipotent entity, typically God. At its core, the paradox challenges the coherence of the idea of omnipotence by posing questions that reveal apparent contradictions. The classic formulation of the paradox is simple but profound. Can an omnipotent being create a rock so heavy that even it cannot lift it? If the being can create such a rock, then there is something it cannot do: lift the rock. If it cannot create the rock, then there is also something it cannot do: create the rock. Either way, the being's omnipotence seems to be undermined. This question highlights a tension in the definition of omnipotence. On one hand, omnipotence is often understood as the ability to do anything. On the other hand, the paradox suggests that some tasks inherently limit this ability, creating a contradiction. It forces us to consider whether omnipotence includes the power to create situations that negate omnipotence itself. To understand this paradox more deeply, let's break it into its key components. First, consider the idea of creating a rock so heavy that it cannot be lifted. This task is paradoxical because it defines a condition that inherently limits the creator's power. If the being creates the rock, it imposes a restriction on itself, contradicting the notion of unlimited power. If the being cannot create the rock, then there is a limit to its creative ability, which also contradicts omnipotence. One way to approach this paradox is to examine the concept of logical consistency. Some philosophers argue that omnipotence does not include the ability to do the logically impossible. For example, creating a square circle or making 2 + 2 = 5 are not tasks that even an omnipotent being can accomplish because they violate the fundamental principles of logic. Under this view, the paradox of the omnipotent being is resolved by redefining omnipotence as the ability to do anything that is logically possible. Creating a rock that cannot be lifted by an omnipotent being is considered a logically impossible task, and therefore falls outside the scope of omnipotence. This perspective is supported by the idea that logical impossibilities are not things that can be done. They are contradictions in terms, and asking whether an omnipotent being can perform such tasks is akin to asking whether it can make a nonsense statement true. For example, if you ask whether an omnipotent being can make a triangle with 4 sides, you are not describing a possible action, but rather presenting a linguistic contradiction. From this standpoint, the paradox dissolves because it is not a valid challenge to the concept of omnipotence. However, not everyone agrees with this resolution. Some argue that omnipotence must include the power to perform even logically impossible tasks, otherwise it is not truly unlimited. This interpretation of omnipotence leads to deeper questions about the nature of power and the relationship between logic and reality. If an omnipotent being can transcend logic, then the paradox of the omnipotent being becomes a demonstration of the limits of human understanding rather than a contradiction. In this view, the paradox is not a flaw in the concept of omnipotence, but a reflection of our inability to comprehend a being that exists beyond the rules of logic. Another approach to resolving the paradox involves redefining omnipotence in terms of internal consistency. This view suggests that omnipotence means having unlimited power within the framework of one's nature or essence. For example, an omnipotent being might be unable to perform self-contradictory actions, not because of a lack of power, but because such actions are meaningless or incompatible with its nature. This perspective allows omnipotence to remain coherent while avoiding the paradox. To illustrate this, consider a different version of the paradox. Can an omnipotent being cease to exist? If the answer is yes, then the being is no longer omnipotent. If the answer is no, then there is something it cannot do. Under the framework of internal consistency, The question becomes irrelevant because ceasing to exist would contradict the being's nature as eternal and all-powerful. Omnipotence, in this sense, does not include the ability to negate itself. The paradox of the omnipotent being also raises questions about the limits of language. When we describe an omnipotent being, we rely on words and concepts that are shaped by human experience and logic. These tools may be inadequate for capturing the essence of omnipotence, leading to misunderstandings and apparent contradictions. Some philosophers argue that the paradox arises not from a flaw in the concept of omnipotence, but from the limitations of our language and thought processes. In theological discussions, the paradox has been used to explore the nature of divine power and the relationship between God and logic. Many religious traditions hold that God is both omnipotent and perfectly logical. Reconciling these attributes requires careful consideration of what it means to be all-powerful. Some theologians argue that God's omnipotence includes the ability to act in ways that are beyond human comprehension, but not in ways that are logically incoherent. Others suggest that God's omnipotence encompasses the ability to perform even the logically impossible, emphasizing the transcendence of divine power. The paradox has implications beyond theology and philosophy. It invites reflection on the nature of power, the limits of human understanding, and the role of logic in shaping our worldview. It challenges us to think critically about the concepts we take for granted and to consider the possibility that some questions may not have definitive answers. In modern discussions, the paradox often serves as a tool for exploring broader questions about authority, responsibility, and self-limitation. For example, in political or ethical contexts, the idea of an all-powerful leader or institution might raise similar dilemmas. Can absolute power exist without undermining itself? What are the consequences of creating conditions that limit one's authority? These questions parallel the issues raised by the paradox of the omnipotent being and highlight its relevance to real-world challenges. In conclusion, the paradox of the omnipotent being is a profound and enduring puzzle that continues to inspire debate and reflection. It challenges our understanding of power, logic, and the limits of human thought, offering insights that go beyond theology and philosophy. Whether viewed as a contradiction, a linguistic problem, or a demonstration of the limits of reason, the paradox invites us to question our assumptions and explore the nature of reality in deeper ways. Simpson's paradox is a fascinating statistical phenomenon where a trend that appears in separate groups of data disappears or reverses when the groups are combined. It is counterintuitive and often surprising, highlighting the importance of understanding how data is grouped and analyzed. This paradox is named after Edward H. Simpson, who described it in a 1951 paper, although the concept had been noted earlier by other statisticians. The paradox typically arises when there is a lurking variable, sometimes called a confounding variable, that influences the relationship between two other variables. This hidden variable can create the illusion of a relationship or obscure the true relationship. Simpson's paradox is not just a mathematical curiosity. It has real-world implications in fields such as medicine, social science, and public policy, where incorrect interpretations of data can lead to flawed decisions. To understand Simpson's paradox, consider a simple example involving two treatments for a medical condition. Treatment A and treatment B. Suppose researchers want to determine which treatment is more effective. The overall data might show that treatment B has a higher success rate than treatment A. However, when the data is broken down into subgroups, such as by age or severity of the condition, it might turn out that treatment A is more effective for every subgroup. This reversal happens because the overall data combines information in a way that masks the underlying trends. Here's how the paradox can play out in more detail. Imagine that a hospital is testing two treatments on two groups of patients: younger patients and older patients. Among younger patients, treatment A has a success rate of 90%, while treatment B has a success rate of 80%. Among older patients, treatment A has a success rate of 70%, while treatment B has a success rate of 60%. Based on these subgroup analyses, treatment A seems better for both groups. However, if treatment B was administered to a much larger proportion of younger patients who tend to have higher success rates overall, the combined success rate for treatment B might appear higher than for treatment A. This happens because the data from the larger group disproportionately influences the overall average. The illusion created by combining the data is the essence of Simpson's paradox. This paradox highlights the importance of considering context and subgroup analysis when interpreting data. Without careful analysis, it is easy to draw incorrect conclusions. In the medical example, a decision to recommend treatment B based solely on the overall success rate would ignore the fact that treatment A is more effective for every subgroup of patients. Simpson's paradox can also appear in other contexts. For example, in education, a school might appear to have lower test scores overall than another school. But when scores are broken down by socioeconomic status, the first school might outperform the second in every category. The apparent disadvantage in the overall scores could be due to differences in the distribution of students across socioeconomic groups. In sports, the paradox can occur when comparing the performance of two players. Suppose player X has a higher batting average than player Y during the first half of the season and also during the second half of the season. Surprisingly, player Y might still have a higher overall batting average if player Y faced more favorable conditions during one of the halves and the distribution of opportunities was uneven. The key to understanding Simpson's paradox lies in recognizing the role of the confounding variable. In the examples above, factors such as age, socioeconomic status, or the number of opportunities influence the overall results. These hidden variables can skew the combined data, creating misleading patterns. To avoid falling into the trap of Simpson's paradox, it's crucial to identify and account for these variables during analysis. One way to address Simpson's paradox is through stratification. This means analyzing data within subgroups rather than relying solely on aggregated data. By examining trends within subgroups, researchers can uncover the true relationships between variables and avoid being misled by combined data. In the medical example, stratifying by age group reveals that treatment A is consistently better, regardless of the overall success rate. Another approach is to use statistical methods that control for confounding variables. Techniques such as regression analysis or propensity score matching can help isolate the effects of different variables, making it easier to understand the true relationships in the data. These methods are especially important in complex studies where multiple variables interact in subtle ways. Simpson's paradox also underscores the importance of transparency in presenting data. When summarizing results, researchers and analysts should disclose how data is grouped and whether subgroup analysis has been conducted. This ensures that conclusions are based on a clear understanding of the underlying patterns, rather than on misleading averages. The paradox has implications beyond statistics and data analysis. It serves as a reminder that context matters in decision-making. Whether in medicine, education, business, or public policy, decisions should be informed by a nuanced understanding of the data, not just by surface-level trends. By considering the broader context and potential confounding factors, we can make better choices and avoid the pitfalls of oversimplification. For instance, consider a hiring decision in a company. If the overall success rate of applicants from one group appears lower than that of another group, it might be tempting to favor the second group. However, if the success rate is influenced by factors like department placement or role requirements, a closer look might reveal that the first group is more qualified for certain roles. Ignoring these details could lead to biased or suboptimal decisions. In conclusion, Simpson's paradox is a powerful reminder of the complexities of data interpretation. It challenges us to think critically about the relationships between variables and to question the assumptions underlying our conclusions. By recognizing the potential for confounding variables and using appropriate analytical techniques, we can avoid being misled by the paradox and uncover the true patterns in the data. Whether you're analyzing statistics or making real-world decisions, Simpson's paradox highlights the importance of digging deeper and considering the context behind the numbers. The prisoner's dilemma in infinite iterations is a thought-provoking scenario that extends one of the most famous problems in game theory, the prisoner's dilemma. It explores how individuals or entities make decisions when they face the same dilemma repeatedly, with no fixed endpoint. Unlike the standard, single-shot version of the prisoner's dilemma, the infinite iteration version introduces new dynamics by allowing players to adapt their strategies over time based on past interactions. This setup reveals fascinating insights about cooperation, trust, and rationality, which are relevant in economics, politics, and even everyday life. To understand the infinite iteration scenario, let's first review the basic setup of the prisoner's dilemma. Imagine two prisoners who have been arrested for a crime. The authorities separate them and offer each a deal. If one betrays the other, defects, while the other remains silent, cooperates, the defector goes free, while the silent prisoner receives a harsh punishment. If both betray each other, they each receive a moderate punishment. If both remain silent, they both receive a light punishment. The dilemma arises because betraying the other seems like the rational choice for both players. No matter what the other prisoner does, defecting always results in a better individual outcome. However, when both prisoners defect, they end up worse off than if they had cooperated. The single-shot prisoner's dilemma illustrates the tension between individual rationality and collective well-being. Now consider what happens when the dilemma is repeated an infinite number of times. In this version, the prisoners interact repeatedly, and each player's decision in one round can influence the other player's behavior in future rounds. The infinite horizon means there is no fixed endpoint, so players cannot base their strategies on an imminent conclusion. Instead, they must navigate a complex interplay of trust, retaliation, and long-term thinking. The possibility of infinite iterations transforms the game. In the single-shot version, defection is the dominant strategy because there are no future consequences to consider. In an infinite iteration setting, however, players can reward cooperation and punish defection over time, creating opportunities for trust and collaboration. This dynamic makes cooperation not only possible, but often advantageous. Let's explore a scenario to illustrate this. Imagine two companies, A and B, operating in the same market. They repeatedly face a decision: to compete aggressively, defect, or to maintain fair pricing, cooperate. If both cooperate, they enjoy steady profits. If one defects by slashing prices, it gains market share, while the other suffers losses. If both defect, they enter a price war, reducing profits for both. In a single interaction, defection might seem like the best choice for each company. However, in an infinite iteration scenario, each company knows that today's actions will influence tomorrow's outcomes. If Company A defects, Company B may retaliate in the next round, leading to a prolonged price war. On the other hand, if both companies cooperate, they can sustain mutual profitability over time. The knowledge of future interactions encourages strategies that promote cooperation, even when short-term incentives favor defection. One of the most famous strategies for the prisoner's dilemma in infinite iterations is tit for tat. This strategy starts by cooperating in the first round and then mirrors the opponent's previous move in subsequent rounds. If the opponent cooperates, tit for tat continues to cooperate. If the opponent defects, tit for tat retaliates by defecting in the next round. This simple approach has been shown to be remarkably effective in promoting cooperation in many scenarios. Its success lies in its balance of kindness and retaliation. It rewards cooperation but punishes defection. However, tit for tat is not without its vulnerabilities. In some cases, a single defection can lead to an unending cycle of retaliation, where both players continually punish each other for past actions. This potential for escalation highlights the importance of strategies that allow for forgiveness. Variants like tit for two tats, which only retaliates after two consecutive defections, introduce more tolerance to mitigate the risk of endless conflict. Another interesting strategy is grim trigger. In this approach, a player cooperates as long as the opponent cooperates, but the first defection triggers permanent retaliation. Grim trigger is highly effective at deterring defection because the cost of losing future cooperation is so high. However, it is also unforgiving. one mistake or misunderstanding can lead to an irreversible breakdown of cooperation. The infinite iteration prisoner's dilemma demonstrates how the shadow of the future shapes behavior. When players value future payoffs highly, they are more likely to cooperate because the benefits of long-term collaboration outweigh the short-term gains of defection. This dynamic is particularly relevant in real-world relationships, whether between individuals, businesses, or nations. Trust, reputation, and the anticipation of ongoing interaction all play crucial roles in fostering cooperation. For example, consider international trade agreements. Countries often face decisions about whether to adhere to trade rules, cooperate, or impose tariffs, defect. In a single interaction, imposing tariffs might seem beneficial for a country seeking to protect its industries. But in an ongoing trade relationship, retaliation from other countries can lead to escalating trade wars, harming all parties. The knowledge of future interactions encourages nations to uphold agreements, even when short-term incentives might tempt defection. Another real-world application is in environmental agreements. Countries must decide whether to reduce emissions, cooperate, or prioritize economic growth, defect. In a one-time scenario, defection might seem rational, as the immediate benefits of industrial expansion outweigh the costs of non-cooperation. However, in the context of ongoing negotiations and the shared consequences of climate change, cooperation becomes a more viable and desirable strategy. The infinite iteration framework helps explain why countries often commit to long-term environmental goals, even when enforcement mechanisms are weak. The infinite iteration prisoner's dilemma also provides insights into human behavior. People often value fairness, trust, and reciprocity in relationships, even when immediate incentives might suggest otherwise. In friendships, partnerships, and communities, the potential for ongoing interaction fosters cooperation and discourages selfish behavior. The paradox of the dilemma is that while rational self-interest might lead to defection in the short term, a broader perspective that includes future consequences often promotes collaborative behavior. However, achieving cooperation in infinite iterations is not guaranteed. The success of cooperative strategies depends on several factors, including communication, trust, and the ability to observe and respond to the other player's actions. Miscommunication or uncertainty about the other player's intentions can undermine cooperation, leading to unnecessary conflict. In such cases, strategies that emphasize forgiveness and flexibility become particularly valuable. In conclusion, the prisoner's dilemma in infinite iterations transforms a scenario of inherent conflict into one of potential cooperation. By introducing the prospect of ongoing interaction, it highlights how trust, reputation, and long-term thinking can overcome the short-term incentives to defect. The insights from this extended dilemma have far-reaching implications, shedding light on how individuals, organizations, and nations navigate complex relationships. It challenges us to think beyond immediate gains and consider the broader context of our actions, emphasizing the importance of collaboration in a world of interconnected decisions. Eternal recurrence, a central idea in Friedrich Nietzsche's philosophy, is the concept that all events in the universe repeat infinitely in the same sequence. This idea is more than a speculative thought experiment. It challenges how we think about time, existence, and the value of our lives. Nietzsche presents it not as a scientific claim, but as a provocative test of one's attitude toward life. By contemplating eternal recurrence, we are forced to confront the meaning of our actions, choices, and existence. The idea of eternal recurrence suggests that every moment you experience now has happened before and will happen again, endlessly. Imagine your entire life, with all its joys, sorrows, and mundane details, repeating over and over without variation. Every decision you make, every triumph, and every regret would recur eternally, with no possibility of change or escape. Nietzsche does not ask whether this is literally true, but instead invites us to reflect on how we would respond to such a scenario. The concept is introduced most vividly in Nietzsche's book The Gay Science, where he writes about a thought experiment. He asks the reader to imagine being visited by a demon who tells them, "This life, as you now live it and have lived it, you will have to live once more and innumerable times more, and there will be nothing new in it but every pain and every joy and every thought and sigh and everything unutterably small or great in your life will have to return to you, all in the same succession and sequence. The demon then poses a question. Would this idea fill you with joy, or would it crush you? Nietzsche uses eternal recurrence as a test of one's love for life. If the thought of reliving your life exactly as it is brings despair, it may suggest that you are not fully embracing existence. On the other hand, if you could accept eternal recurrence with joy, it would mean that you affirm your life completely, including its struggles and imperfections. Nietzsche refers to this affirmation as amor fati, or the love of fate, the idea that one should embrace everything that happens, seeing it as essential to the beauty and meaning of life. This concept ties deeply into Nietzsche's critique of traditional morality and his vision of human potential. He challenges us to live in a way that would make eternal recurrence not a curse but a blessing. To achieve this, we must overcome feelings of resentment, regret, and escapism. Nietzsche believed that many people avoid confronting the reality of their lives by looking to external sources of meaning, such as religion or an imagined afterlife. Eternal recurrence removes these crutches, forcing us to face life as it is and to find meaning within it. The idea also reflects Nietzsche's broader philosophy of life affirmation. He rejects the notion that suffering and imperfection diminish the value of life. Instead, he sees them as integral to existence and essential to growth and creativity. By embracing eternal recurrence, we acknowledge that life, with all its complexity, is worth living, not because it leads to some ultimate reward, but because it is valuable in itself. To make this more relatable, consider how you might respond if you knew that your life would repeat endlessly. Would you change the way you live? Would you focus more on pursuing your passions, cherishing your relationships, or finding joy in the present moment? The thought of eternal recurrence pushes us to think about what truly matters and to evaluate whether we are living authentically. For example, imagine a person who spends most of their time in a monotonous job they dislike, postponing happiness for some vague future goal. If they were told that this exact life would repeat forever, they might realize the need to make a change, whether by seeking a more fulfilling career, cultivating meaningful relationships, or finding joy in the present. Eternal recurrence acts as a mirror, reflecting the choices we make and urging us to live with greater intentionality. Nietzsche's idea also challenges the linear view of time and progress that dominates much of Western thought. In traditional religious and philosophical frameworks, time is often seen as a journey with a clear beginning and end point, such as creation and salvation. Eternal recurrence, however, presents time as cyclical and endless, without a final goal or ultimate purpose. This challenges us to find meaning not in a distant future, but in the here and now. Critics of eternal recurrence often question its practicality and coherence. Some argue that it is purely speculative and has no basis in reality. Others see it as a pessimistic view, reducing life to an endless repetition without progress. However, Nietzsche's intent is not to prove eternal recurrence as a literal truth, but to use it as a tool for self-reflection and transformation. The power of the idea lies in its ability to shift our perspective, not in its empirical validity. Philosophically, eternal recurrence aligns with Nietzsche's rejection of absolute truths and his embrace of perspectivism. He challenges us to see life not as something to be judged by external standards, but as something to be lived fully and creatively. Eternal recurrence forces us to confront the question, if I must live this life forever, how can I make it worth living? The concept also resonates with existentialist themes. Like existentialist thinkers such as Jean-Paul Sartre and Albert Camus, Nietzsche emphasizes individual responsibility and the absence of inherent meaning in life. However, while existentialism often focuses on the absurdity of existence, Nietzsche's eternal recurrence offers a more affirmative vision. By embracing the idea, we transform the eternal repetition of life into an expression of joy and creativity. In modern contexts, the idea of eternal recurrence can serve as a metaphor for mindfulness and intentional living. In a world dominated by distractions and future-oriented thinking, it reminds us to focus on the present and to live as if every moment matters. It challenges us to break free from cycles of regret, anxiety, and complacency, encouraging us to see each action as meaningful and each experience as valuable. Consider, for instance, how this idea might influence someone struggling with regret over past mistakes. The thought of reliving those moments indefinitely could feel unbearable. However, by embracing eternal recurrence, they might come to see those mistakes as essential to their growth and understanding. Rather than wishing for a different past, they could learn to accept and even appreciate the experiences that have shaped them. Eternal recurrence also has implications for how we view success and failure. In a world obsessed with achievement, the idea challenges us to reconsider what truly matters. If life is an endless cycle, external markers of success, such as wealth, status, or fame, may lose their significance. What remains is the quality of our experiences, relationships, and the ways in which we engage with the world. In conclusion, eternal recurrence is a profound and challenging concept that invites us to reflect on the nature of existence and the value of our lives. By imagining life as an infinite repetition, Nietzsche forces us to confront our choices and attitudes, pushing us toward greater self-awareness and authenticity. The idea is not meant to be taken as a literal truth, but as a tool for transformation, encouraging us to embrace life fully and to live in a way that affirms its worth. Whether seen as a philosophical puzzle, a moral challenge, or a call to mindfulness, eternal recurrence remains one of Nietzsche's most powerful and enduring contributions to the exploration of human existence. Hofstadter's strange loop is a concept introduced by cognitive scientist and philosopher Douglas Hofstadter in his book Gödel, Escher, Bach, and Eternal Golden Braid. The idea explores how systems can contain self-referential structures that seem to loop back on themselves, creating a paradoxical sense of hierarchy and circularity. These strange loops often challenge our understanding of order, meaning, and self-awareness. Hofstadter uses the concept to delve into topics like consciousness, mathematics, and art, offering a framework for understanding phenomena where the boundary between levels of structure becomes blurred. At its core, a strange loop occurs when a system moves through a hierarchical structure in a way that eventually leads back to its starting point. Imagine climbing a spiral staircase in a tower, expecting to ascend higher with each step, only to find yourself back where you started. The loop creates the illusion of progression or ascent, but ultimately circles back to the beginning. This kind of structure is central to Hofstadter's exploration of how meaning arises and how complex systems, like the human mind, function. Hofstadter draws on examples from diverse fields to illustrate the concept. In mathematics, the idea of a strange loop is famously embodied in Gödel's incompleteness theorems, which demonstrate that any sufficiently complex formal system can reference itself in a way that creates statements it cannot prove. This self-reference creates a loop within the logical framework, revealing limits in the system's ability to fully describe itself. A simpler example can be found in linguistic self-reference, such as the sentence, "This statement is false." This sentence creates a paradox because its truth depends on its own content. If it is true, then it must be false. If it is false, then it must be true. The sentence loops back on itself, creating a strange loop that resists resolution. Similarly, in art, the work of M.C. Escher, such as his famous drawings of staircases that endlessly ascend or descend, provides a visual representation of strange loops. These images create a sense of motion or progression within a system that paradoxically circles back to its origin. The most profound application of the strange loop, however, is in Hofstadter's exploration of consciousness. He argues that the human mind itself is a kind of strange loop, where self-awareness arises from a complex system of interacting levels that ultimately refer back to themselves. In his view, the brain processes information in layers, with each layer contributing to a sense of identity and selfhood. This recursive process creates the feeling of I, or the sense of being a unified self. To make this more relatable, consider how you think about your own thoughts. When you reflect on your feelings or ideas, you create a feedback loop in which your mind becomes both the observer and the observed. This self-referential process gives rise to the experience of being a conscious individual. Hofstadter suggests that this loop is not a mere metaphor, but the actual mechanism by which consciousness emerges. The self, in this sense, is not a static entity but a dynamic process, a strange loop that perpetually constructs and reconstructs itself. Strange loops also challenge our understanding of hierarchy. In most systems, higher levels are distinct from lower levels, with clear boundaries separating them. For example, in a company, employees report to managers, who report to executives, creating a clear chain of command. A strange loop, however, disrupts this hierarchy by allowing lower levels to influence higher levels in unexpected ways, or by collapsing the distinction between levels altogether. This disruption is not just theoretical. It has practical implications for understanding complex systems, from organizations to ecosystems to neural networks. To see this in action, think about a thermostat. On the surface, it seems like a simple system. The thermostat senses the temperature input, compares it to the desired setting, processing, and adjusts the heating or cooling system accordingly, output. But if the thermostat could reflect on its own settings and adjust its behavior based on how well it regulates the temperature, it would create a feedback loop, a rudimentary form of self-reference. While a thermostat lacks the complexity of human consciousness, it illustrates how even basic systems can exhibit the principles of strange loops when they interact with themselves. Strange loops also appear in storytelling and culture. Consider narratives where characters become aware of their own roles within a story. In films like The Truman Show or Inception, the characters confront the boundaries between reality and fiction, creating loops where the story folds back on itself. These meta-narratives invite viewers to question their own assumptions about reality and meaning, much like Hofstadter's strange loops do in philosophy. The concept of a strange loop also has implications for artificial intelligence. If human consciousness is indeed a strange loop, as Hofstadter suggests, then creating artificial intelligence that mimics human thought may require designing systems capable of self-reference and recursive processing. This idea raises profound questions about the nature of intelligence and whether machines can truly replicate the experience of self-awareness. Can an artificial system create its own strange loop, or is consciousness inherently tied to biological processes? Critics of the strange loop concept sometimes argue that it is too abstract or speculative. While the idea is compelling, its application to fields like neuroscience and artificial intelligence remains theoretical. Skeptics question whether the concept can be tested empirically or whether it serves primarily as a metaphor for complex phenomena. Nevertheless, the strange loop remains a powerful framework for exploring questions about systems, selfhood, and the nature of reality. In practical terms, understanding strange loops can change the way we think about problem-solving and decision-making. Many real-world challenges involve feedback loops, where actions and outcomes influence each other in complex ways. Recognizing these loops can help us navigate situations where linear thinking falls short. For example, in environmental policy, addressing climate change requires understanding the feedback loops between human behavior, economic systems, and ecological processes. These interconnected loops often defy simple solutions, requiring approaches that account for their dynamic and recursive nature. Strange loops also invite us to think differently about identity and relationships. If the self is not a fixed entity but a process of constant self-reference, then our sense of identity is fluid and shaped by interaction with others. This perspective challenges traditional notions of individuality, suggesting that we are deeply interconnected with the systems and people around us. In conclusion, Hofstadter's strange loop is a profound and versatile concept that bridges disciplines, from mathematics and art to philosophy and neuroscience. It challenges our understanding of hierarchy, meaning, and self-awareness, offering a framework for exploring the recursive nature of complex systems. Whether applied to the workings of the mind, the structure of language, or the dynamics of society, the strange loop reveals how self-reference and feedback create patterns that are at once paradoxical and deeply meaningful. By reflecting on these loops, we gain insight into the nature of consciousness, the limits of logic, and the interconnectedness of all things. A tautology is a statement that is true in every situation, no matter the circumstances. At first glance, tautologies might seem simple or harmless, They are often seen as empty truths, statements that add no new information or meaning. For example, the statement, "It will either rain tomorrow or it won't rain tomorrow," is a tautology. It cannot be false because it covers all possible outcomes. However, when you look deeper, tautologies can reveal surprising insights about logic, communication, and even human reasoning. They can also lead to a sense of infinite redundancy, where a process or conversation loops endlessly without progressing or changing. Imagine a conversation where someone keeps saying, "If we follow the rules, we will follow the rules." This statement is true, but it does not actually tell you anything useful. It does not add knowledge or clarify the situation. Instead, it circles back on itself, repeating a truth that was already obvious. This circular nature is what creates the feeling of redundancy. A tautology like this can feel like an infinite loop, where logic folds back on itself without ever providing a deeper understanding. To explore this idea further, think about mathematical or logical systems. In logic, a tautology is a statement that is true by definition. For instance, the statement, "A or not A" is always true. If A represents a condition, like the light is on, then A or not A means the light is either on or not on. There is no situation where this statement could be false because it covers all possibilities. While this might seem trivial, tautologies play a key role in formal logic. They form the backbone of proofs and arguments by establishing a framework of unbreakable truths. Without them, logical systems would lack consistency and reliability. However, in everyday language, tautologies can be frustrating. They can make discussions feel repetitive or unproductive. Imagine someone asks, "Why should we trust the system?" And the answer is, "Because the system works if it works." This response is technically true, but it offers no real explanation. It simply restates the question in a different form. The conversation becomes stuck in a loop, where the reasoning never advances or addresses the deeper issue. This is one of the main problems with tautologies in practical contexts. They can derail meaningful discussions and leave people feeling unsatisfied. Another common example of tautologies creating infinite redundancy appears in politics or advertising. Politicians often use tautological statements to appear confident without committing to anything specific. For example, a politician might say, "We will win if we work together." This statement is true by definition. Cooperation often leads to success. However, it does not provide a clear plan or actionable steps. Instead, it creates the illusion of progress while essentially saying nothing new. Similarly, advertisers might use tautologies to make their products seem appealing without providing real information. A slogan like, "The best quality is quality you can trust," sounds reassuring, but it is a circular statement that adds no real value. Tautologies also play a role in how people justify their beliefs. When someone strongly believes something, they might unconsciously rely on tautological reasoning to defend their position. For instance, a person might say, "I know this is true because it feels true." This statement does not explain why the belief is valid. It simply restates the belief in a different form. This kind of reasoning can create an echo chamber, where beliefs are reinforced without being questioned or tested. The same logic applies to groupthink, where a community collectively affirms its own beliefs through tautologies, creating a cycle that resists outside perspectives. Even in storytelling, tautologies can create infinite loops. In some poorly written narratives, characters or plot lines might rely on tautological reasoning to justify their actions. For example, a character might explain their behavior by saying, "I did it because I had to do it." This reasoning offers no insight into the character's motivations or the circumstances that led to their choice. Instead, it creates a closed loop that prevents the story from exploring deeper themes or conflicts. While this might work in certain contexts, such as portraying a character trapped by fate or duty, it can also make the narrative feel shallow or unengaging. To understand why tautologies can feel so frustrating, it helps to think about how the human mind processes information. People seek meaning and connections in what they hear or read. They want explanations that help them understand the world or solve problems. When a statement is tautological, it breaks this expectation. Instead of providing new information, it reflects back what was already known. This can create a sense of stagnation, as if the conversation or thought process is going in circles. In extreme cases, this can even lead to mental fatigue or disengagement, as the brain struggles to find value in the repetition. Tautologies also reveal something important about the limits of language. In theory, language is a tool for communication and understanding. It allows people to express complex ideas, share knowledge, and solve problems together. But when language becomes tautological, it loses its power to convey meaning. It becomes self-referential, folding back on itself in an endless loop. This shows how language, while incredibly powerful, can sometimes fall short of its potential. It reminds us to be mindful of how we use words and to strive for clarity and depth in our communication. In some cases, tautologies can even create paradoxes. For example, consider the statement, "Everything that exists, exists." This is a tautology because it is always true. However, if you try to analyze it deeply, you might start questioning what it means for something to exist. Does it include abstract concepts like numbers or ideas? Does it apply to hypothetical scenarios or parallel universes? These questions can lead to an infinite loop of philosophical inquiry, where the original tautology becomes a springboard for deeper and more complex debates. Another example of tautologies creating paradoxes is the phrase, "It is what it is." This statement is often used to express acceptance or resignation, but it is also a tautology. It does not actually explain or clarify anything. Instead, it restates itself in different words. This can lead to confusion or frustration, especially if someone is looking for a deeper explanation or resolution. In some cases, the phrase might even be used to avoid addressing difficult issues, creating a sense of avoidance or denial. Despite their limitations, tautologies do have their place. In certain contexts, they can serve as useful reminders of basic truths or principles. For example, the statement, "Practice makes perfect," is a tautology in some ways. It suggests that repetition leads to improvement, which is self-evident. However, it can still be a helpful motivator or guiding principle for someone trying to develop a skill. Similarly, tautologies can be useful in teaching or explaining concepts, as they provide a starting point for building more complex ideas. In science and mathematics, tautologies are often seen as building blocks. They provide a foundation of absolute truths that can support more complex theories and calculations. For instance, the law of identity in logic states that A equals A. This might seem trivial, but it is a fundamental principle that underlies all reasoning. Without it, logical systems would collapse into inconsistency and chaos. In this sense, tautologies are not just redundant, they are essential. However, the challenge lies in recognizing when tautologies are helpful and when they become a hindrance. In everyday life, tautologies can easily slip into conversations or arguments, creating loops that go nowhere. To avoid this, it helps to ask questions that challenge assumptions or explore deeper meanings. Instead of accepting a tautology at face value, try to unpack it and see what lies beneath. This can lead to more productive and meaningful discussions, where ideas are tested and refined rather than endlessly repeated. In conclusion, tautologies and infinite redundancy are fascinating aspects of logic and communication. They reveal the power and limitations of language, the challenges of reasoning, and the ways people justify their beliefs. While tautologies can sometimes feel frustrating or unproductive, they also have their uses, especially in formal systems like mathematics and logic. By understanding how tautologies work and recognizing their impact, we can use them more effectively and avoid getting stuck in endless loops of repetition. Ultimately, this awareness helps us communicate more clearly, think more critically, and engage more deeply with the world around us. The Omnipotence paradox of free will explores a conflict between the idea of a supreme, all-knowing being and the existence of free will. To understand this, imagine a situation where someone claims to know every decision you will ever make before you make it. If this is true, how can your choices truly be free? The paradox arises because the idea of complete knowledge seems to undermine the ability to choose freely. Start by thinking about what it means to have free will. Free will means having the power to make choices that are not entirely determined by external factors, internal instincts, or divine intervention. When you decide what to eat for breakfast, it feels like your choice. You could choose toast or cereal, and you believe the choice is yours to make. Now imagine someone who knows in advance that you will pick toast. Could you still say you freely chose it? The fact that the choice was already known seems to imply it was inevitable. This problem becomes more complex when you introduce an omnipotent being. Such a being is often described as knowing everything, including all future events. If they know in advance what you will do, can you really claim to have freedom? Let's say this being knows that tomorrow you will choose to skip lunch. At first, this might seem harmless, but the moment you try to assert your freedom by choosing to eat lunch instead, it creates a conflict. If the being's knowledge is infallible, they would have known you would choose lunch. It suggests that no matter what you do, your actions are already known. If they are already known, can they be truly free? To explore this further, consider a hypothetical scenario. Imagine a person named Alex. Alex has always believed in free will. One day, Alex meets someone who claims to know everything about Alex's future. This person, let's call them Jordan, tells Alex, "Tomorrow at 3 p.m., you will decide to buy a coffee." Alex, feeling stubborn and wanting to prove Jordan wrong, decides to avoid coffee altogether. But at 3 p.m. the next day, Alex suddenly feels thirsty and, almost without thinking, buys a coffee. Jordan smiles and says, "I told you so." Alex feels trapped. Was the choice really free? If Alex had decided not to buy coffee, Jordan might have predicted that instead. Either way, it feels like Alex's choices are constrained by what Jordan knows. But why? The key issue lies in the relationship between knowing and causing. Does Jordan's knowledge of Alex's future cause Alex to act that way? Or does Jordan simply know what Alex will freely choose to do? The distinction is subtle but important. If knowledge alone does not cause actions, then Alex's choice to buy coffee could still be free. In this case, Jordan's knowledge is more like seeing into the future than controlling it. However, the problem doesn't disappear entirely. For Alex, the feeling of freedom is tied to uncertainty. If Alex always knew Jordan's predictions would come true, it would feel as though Alex had no power to change anything. Even if Jordan didn't cause the outcome, Alex might struggle to feel truly free. Now think about this in the context of an omnipotent being. Unlike Jordan, this being doesn't just predict Alex's actions, but knows them with perfect certainty. This knowledge isn't based on a guess or a calculation, but is considered absolute. If you expand the scenario to include everyone in the world, it raises even more questions. If every choice, from the smallest decision to the most significant action, is already known, how can anyone claim to have genuine freedom? One way to address this paradox is to argue that free will and foreknowledge can coexist. This view suggests that knowing something in advance doesn't mean causing it to happen. For example, imagine watching a recording of yesterday's weather. You know that it rained at 4 p.m., but your knowledge didn't cause the rain. In the same way, an omnipotent being might know the future without interfering in it. This approach, called compatibilism, argues that foreknowledge and free will are not necessarily contradictory. However, this explanation raises its own questions. The weather analogy works because the recording is about the past. With the future, the situation feels different. If the future is already known, it can feel as though it is fixed. A fixed future might seem to leave no room for freedom. Imagine you are reading a book where the ending is already written. Even if you don't know the ending yet, it exists. The story cannot change once it's printed. If the universe works like that book, how can your actions be free? The idea that the future is written can make the concept of free will feel like an illusion. Another approach to resolving the paradox is to reconsider what omnipotence and omniscience mean. Some thinkers argue that omnipotence doesn't require knowing every detail about the future. Instead, it could mean having the power to know anything, but not necessarily exercising that power in every case. In this view, an omnipotent being might choose not to know what you will do in certain situations. This creates space for free will, as the future is not entirely predetermined. Others go further, suggesting that omniscience might involve knowing all possible outcomes rather than a single fixed future. Imagine a branching tree where each branch represents a choice you could make. An omniscient being might know all the branches and where they lead, but not necessarily force you to take one branch over another. This idea aligns with the concept of open theism, where the future is seen as open and not entirely fixed. The paradox also challenges our understanding of time. In our daily lives, we think of time as linear, moving from past to present to future. However, an omnipotent being might experience time differently, seeing all moments simultaneously. From this perspective, the being's knowledge of the future doesn't come from looking ahead, but from seeing everything at once. If this is true, the being's knowledge might not conflict with free will because it exists outside the timeline we experience. To see this differently, think of an observer standing on a hill watching a parade. The observer sees the beginning, middle, and end of the parade all at once, while someone on the ground only sees one part at a time. In this analogy, the observer on the hill doesn't interfere with the parade. They simply have a broader view. If an omnipotent being views time this way, their knowledge might not limit your choices. Instead, it reflects a perspective we can't fully comprehend. Critics of this idea argue that it still doesn't resolve the tension. If the being already sees what you will choose, it seems like your choices are inevitable. This inevitability can feel incompatible with true freedom. The paradox continues to challenge philosophers and theologians because it touches on deep questions about how the universe works and what it means to be free. One more way to approach the paradox is to think about the nature of choice itself. What does it mean to choose freely? Some philosophers argue that free will doesn't require the ability to do otherwise. Instead, it might mean acting in accordance with your desires and reasoning without external coercion. In this view, even if an omnipotent being knows what you will choose, the choice could still be free as long as it aligns with your true self. For example, if Alex buys coffee because Alex genuinely wants coffee, the choice might still be considered free, even if it was known in advance. The omnipotence paradox of free will forces us to confront questions about knowledge, causation, and time. It shows how challenging it is to reconcile the idea of an all-knowing being with the human experience of freedom. Different perspectives offer partial answers, but no single solution resolves the paradox entirely. Instead, it invites ongoing reflection on the nature of existence and the limits of human understanding.